Hello. We are going to stick to a tight schedule just to give everyone the flexibility to move from one room to another and see the presentations they want to see. So we do have some guests with us. It's great to see some non-students joining us. Just to make you aware, all the questions from the audience, we'll have a time for that, but those need to be handled through the chat window. So if you have a question, just type your question over there and I'll moderate that. And then also in the chat window, there is a link for you to enter feedback for the students who are presenting. So when you go to that form, you'll indicate what your role is, faculty, staff, student, visitor, and then which presentation you're evaluating. So Parker, I think we're getting close to 1 o'clock. If you want to go ahead and share your screen with us.
All right, and then just let me know when you want me to start.
Okay, well, I think it's 1 o'clock, so we'll let you go.
All right. Well, hello, everyone. My name is Parker Willman, and my capstone project this year was on glucose regulation using an intelligent PID controller, and my faculty advisor was Dr. Evans. For my presentation today, I'm just going to go through a brief introduction about my project and why I did it. I'm going to talk about the model that I used for my simulations. I'm going to show some preliminary simulations or simulations that were done before my controller was implemented. I'm then going to show you some simulations after my controller was implemented, and then I'm going to finish with some concluding remarks. So for the introduction, many of you have probably heard about diabetes before, and that's because about 10% of the United States population suffers from diabetes. Now, about 5% of these people have type 1 diabetes, which is diabetes that is characterized by the patient's inability to produce their own insulin and therefore cannot maintain their own blood sugar levels without outside intervention. Now, the current standard of treatment for this condition is an artificial pancreas. And this is a multi-component system that has a glucose sensor, usually placed on the arm, that takes blood sugar readings. These readings are then sent to a phone, which runs it through a control algorithm. The algorithm then says this much or X amount of insulin should be injected into the bloodstream. And that amount is sent to an insulin pump, which pumps that insulin into the patient. Now, one potential algorithm for this is a PID-driven system. Now, at this point, you may be wondering, what is a PID controller? Well, it stands for proportional, integral, and derivative. And so it has 3 different components. The proportional component looks at the error between the target glucose and the current glucose levels at a given moment in time. Then the integral component looks at the integral of the error function, or how wrong has the glucose been for how long. And then the derivative component looks at the rate of change of the glucose level itself. As for the model, it is a 13 component differential equation, system of differential equations. Now, there are a lot of different parameters within this system, and I won't go into too much detail right now. I'm going to gloss over it a little bit. Just know that some of the parameters have fixed values and some have a range of values, and I'll be talking about that range later on. So this first set of 3 equations is the insulin kinetics. This is how the insulin moves from where it is injected into the body into the bloodstream. Now this UI right here is the insulin that the controller will be injecting into the patient. This I down here is the concentration of insulin within the patient's bloodstream. And so this value is used to determine if too much insulin is being injected to ensure that the patient does not suffer from insulin poisoning. The next set of 3 equations is the insulin dynamics. This is how the insulin reacts with the body itself. The next set of 3 equations is the glucagon kinetics. So for blood sugar, we consider a compound called glucose, and the precursor to glucose is glucagon. Now, in a diabetic patient, they do not generate their own glucagon in the same way that a healthy person does. So it's possible for the blood sugar to drop too low at times, especially at night. And I'll show some simulations with this later on, but for now, just know that this UG right here is the controller's ability to inject glucagon into the bloodstream to make sure the blood sugar does not drop too low. So this set of equations is just how the glucagon moves from wherever it is being injected into the bloodstream, similar to the insulin. The next three equations are the Glucagon Dynamics. This governs how the glucagon interacts with the body, as well as other compounds within the blood. Finally, we come to the Glucose Kinetics. These two equations are about how the glucose equilibrates between different compartments in the body. The Q1 is the component we care about. That is the amount of sugar in the blood, and it's what we'll be measuring and trying to control throughout the rest of this presentation. So here is a simulation of what would happen to a diabetic patient if they just went about their day with absolutely no insulin. Just a little bit of preliminary information. The day starts in this simulation at 7 a.m. where they have their first meal, and then they have another meal for every 5 hours after that before going to bed. So they get a meal at 7 a.m., 12 p.m., and 5 p.m. before going to bed. As you can see here, by a little while after dinner, the patient has a blood sugar level of about 650 milligrams per deciliter, which is the standard unit of measurement for people with diabetes. But this is an extremely unhealthy level of blood sugar to have. But as you can see, as the night progresses, their blood sugar drops very rapidly before hitting zero before the next morning, and therefore the patient dies. Obviously, we don't want this to happen, so that's the purpose of this system. But how does the system work? Well, the median values for all of those physiological parameters are used by the controller. All the different values that have ranges, the controller takes the median value and just works from there. As the simulation runs, a random value is chosen for a patient from each of those different ranges. Therefore, every patient that is generated by the system is different, and the system cannot be catered to one specific type of patient. Then every 5 minutes, a measurement is taken to fit the system to the patient's blood sugar. And I'll show over the next couple slides why that's important. And then finally, the controller gains are changed after every meal to more accurately guide the system's behavior, or the amount that we weight the proportional, integral, and derivative values of the controller are changed in order to mimic the patient's system more accurately. So this is what happens if we do not take those measurements of what the patient's blood sugar is. As you can see, the simulation shown by the blue line diverges fairly quickly from the patient, the red line. Because the simulation is so high, the controller says we need to inject more insulin, and this causes more insulin to be pumped into the patient than they need, dropping their blood sugar even further. So obviously we need to take a bit of sampling, but the amount of sampling can also be shown about why I chose 5 minutes as my sampling rate. Here I show 30 minutes, and these blue lines, the difference here is what the simulation thinks is happening before it takes the measurement to start running for the next 5 minutes. As that is occurring, you end up seeing a fair amount of difference between the simulation and the patient ends up hitting a blood sugar of 0 milligrams per deciliter before they even reach lunch. However, if you take a 5-minute sampling rate, you get a much more accurate representation of the patient's blood sugar via the simulation. As you can see here, these little error here is much less significant than in the previous slide. Now, this and the next slide are some early simulations that I did with a controller in place. And this is important just to show the variation that occurs between different patients and the different factors that I had to include in my simulations. So as you can see here, one patient is getting their insulin throughout the day, and their blood sugar never drops below 60 milligrams per deciliter. This is a fairly healthy range, and this is pretty much what we would want to see. However, another patient who's being treated with the exact same controller ends up dropping down below 50 milligrams per deciliter pretty readily, and they end up dying before dinner time, or at least being sent to the hospital. So this is something that the controller has to take into account. Because patients have very different physiological parameters, it has to account for these without knowing what those parameters are itself. So this is an example of what happened with the fully functional insulin controller. The glucagon was not implemented at this time. The insulin is injected, and the blood sugar gets up to a little bit above 350 milligrams per deciliter. This is higher than we would like, but it's still better than the initial 650 that we saw without any insulin whatsoever. and it drops down to a little bit above 100. Again, higher than we would like, but still better than the non-insulin outcomes. And as you can see, the oscillations actually get a little smaller as time goes on. And the hope would be that as this simulation was run more and more, that the treatment would converge and we would get a bit less oscillation between these two values. However, the blood sugar still drops down to 0 after dinner time, which is why we have to inject the glucagon. But before I go on to that, I just want to say, if you look here, this is a zoomed in picture. The blue error bars, if you look very closely, you can see the blue simulation kind of spiking up a little bit, but it's much less significant than the earlier simulations, just to show how quickly the system is adapting to the behavior of the patient's body and how well it is able to mimic it as time goes on. The last simulation is just with the Glucagon controller. As you can see here, the glucagon oscillates around 100 milligrams per deciliter, which is exactly where we would want it to be. The delay between the glucagon and the blood sugar is much smaller than the time delay between the insulin and the blood sugar, and that's why these oscillations are much smaller, because the system can react much more quickly. So in conclusion, I just want to say the body is an incredibly complex system to model and control. It's impressive that these 13 equations were ever created by these researchers, but it is an even more difficult system to control. I went into this project thinking that not that it would be simple, but that it would be easily understandable, and I quickly found out I was very wrong about that. And it gave me a new appreciation for the research that is being done by these scientists at this time. PID controllers are also not the most reliable method to control glucose levels in and of themselves. The derivative gain is set much higher than the integral gain, because you want insulin to get to the bloodstream quickly so that the blood sugar does not spike, whereas the integral floods the body with insulin after the fact, which can drop it very quickly. And just the way the system is set up does not make it the ideal system for controlling blood sugar levels. And because of this fact, model predictive control is what a lot of scientists are working toward right now using artificial intelligence, and it's for good reason. The system can tell expect what is going to happen before you even start to digest the meal, and therefore can get a much more accurate representation of what is going to happen over the next couple hours as the body ingests this sugar. These are the references that I used for my presentation. That is all I have at this time. So if you have any questions, now is the time to ask.
Thanks so much, Parker. Great job. As a reminder to the audience, you can submit your questions through the chat window. Anybody have questions for Parker? Okay, no questions. Again, oh, here's one from Dr. Walters. Would you pick this to do again?
I probably would. This is the kind of research that I would like to do going forward. Obviously, if I were to pick it again, I probably wouldn't use PID. However, that is what I have experience with. I don't have any experience with artificial intelligence or model predictive control, but I did take physiological control systems earlier in my senior year. So I did have a little bit of experience with, so while it wasn't the ideal, it is what I had experience with, and it is what I could do. Okay, so yes, but not quite that way.
Other questions for Parker? Don't forget to enter your feedback on Parker's presentation over on the Google form. The link is in the top of the chat. Okay, I'm not seeing any. Go ahead, Parker.
I was going to say, should I stop sharing now?
I think you can stop sharing now. I don't see any other questions coming through. So thank you very much.
Thank you.
I'll do the hand claps again. All right, next up we have Chris Cano. I'll go ahead and make him a co-host. We will wait just a couple of minutes before we start, but Chris, you're welcome to go ahead and share your screen if you want. All right, Chris, I have that it's 1:15, so we'll let you get started.
Yes, ma'am. So my name is Christopher Cano, and my senior capstone project was on the SIR models, their applications, and approximations of their rates. So just a brief outline of this presentation. We're going to get into the introduction of the SIR model, so what it is and who developed it. Then we'll get into the assumptions of the SIR models. Then one of the most common SIR models, the Camac-Mackendrick model, and also the SI model. Then we'll look at the approximations of the SIR models rates. After that, we'll see the SIR models with some real-world data. But first, we're going to look at the focus of this research. So the first focus of this research is to examine two types of SIR models. The two that we'll see in this presentation are the Camac-Mackendrick and the SI models. Then we're going to determine and elaborate on the parameters of each model. So this includes the infection and recovery rates. And then we're going to compare the models to some real-world data. Some real-world data that I have is HIV and COVID-19. So an introduction of the SIR model. It was developed by Sir Ronald Ross. Its purpose is to help predict how diseases will spread based upon several parameters. The model consists of a system of three coupled nonlinear ordinary differential equations. The SIR model is a class of models that predicts the spread of diseases, and these models themselves actually have several assumptions. The first assumption is a fixed population. That means it is assumed that there are no births or no deaths during the duration of the disease. The second one is an incubation period of 0. It means as soon as you begin to show symptoms, you can immediately begin to infect others after obtaining the disease. The third one is the time of being infected is equal to the length of the disease. That's just saying that if you have the disease, then you are indeed in the infected category. And the last one is an assumption of a homogeneous population. And that's just when everyone's assumed to be the same age, same health, and same social status. So each SIR model is designed for specific communicable diseases. And what I mean by communicable disease is just a disease that can be passed from one person to another. The Camac-Mackendrick is designed for diseases that you obtain a lifetime immunity after you recover from the disease. Down here we have the infection rate, and that is the probability that an interaction between an infected and a susceptible individual will result in another infected. And we have the recovery rate right here, and the recovery rate is approximately 1 over D, with D being the average duration of the disease. And here are our variables. We have S, I, and R, which are respectively the percentage of the population susceptible, infected, and that have recovered from the disease. So here's one of the main properties of the Camac-Mackendrick model. it's the epidemiological threshold. So we have the infection rate multiplied by the fraction of the population susceptible at a given time over the recovery rate. Now, if this rate is, well, if this threshold is less than 1, then each infected person will infect at most one other person before dying or recovering. But if this threshold is greater than 1, then each infected person infects 2 or more people, which will cause an exponential rise in the number of infected. So here is just an example of the Camac-Mackendrick model being used. We have a total population of 10,002 with an infection rate of 0.8 and a recovery rate of 0.5. So that means the disease lasts an average of 2 days. Here are our initial conditions: initial 10,000 susceptible, initial 2 infected, and initial 0 recovered. And after 25 days, we can see that the disease will no longer be considered an epidemic. And after the number of infected reaches approximately 0, we can see that 35% of the population would have never contracted the disease, with about 65% of the population having recovered from the disease. Now let's take a look at the SI model. So notice that the setup of the SI model is similar to that of the Camac-Mackendrick model. The SI model, however, does not have a recovered category or a recovery rate. This is due to the fact that the SI model is used on communicable diseases that cannot be recovered from. Before we look at some real-world data, we will see how the infection and recovery rates were approximated. So it was compared the observed data to the expected values. So since the SIR model has no explicit solution, the ODEs, or ordinary differential equations, were solved separately and not as a system. And then we place the solutions of the ordinary differential equations into Excel, then compare the infected category, which will be our expected, to the real-world data we obtained, which will be our observed. Then we use Excel to minimize the actual error by optimizing the infection rate and the recovery rate. From there, we will use our optimized infection rate or infected category and real-world data to determine our chi-squared statistic. Then we used Excel to calculate the p-value from the chi-squared statistic. So our p-value is the probability of our null hypothesis not being rejected. The null hypothesis of a chi-squared goodness of fit test assumes no significant difference between the observed and the expected values. Our p-values for both sets of data we will see is 1. So therefore, we have 100% probability of the null hypothesis not being rejected. Thus, for both sets of data we will see, we find no significant difference between the observed and the expected values. So right here we have HIV in South Africa during 2002 all the way to 2018. We have our infection rate, our total population, our initial conditions, our actual error, and our chi-squared statistic. And we can see about after 58 years after 2002, around 50% of the population will have contracted HIV. And then based on this model, after 120 years after 2002, around 93% of the population will have contracted HIV. So these models don't work too well with small percentages, or that I could find work too well with small percentages. So this has taken the assumption that Rome has Italy's case count. So I used Rome's population because the case count is too small for the model to be accurate. So all in all, kept the number of cases, but reduced Italy's population to that of Rome's. So we have our infection rate and our recovery rate, our total population, initial conditions, and we can see right here that after day 55, the disease is no longer considered an epidemic in Rome, and that's about where the peak is of the infected category, our actual error, and our chi-squared statistic. And we can see that when the number of infected is approximately 0, we have about 42% of the population will have recovered from the disease, with about 58% of the population having never contracted the disease. Okay, so this is just a conclusion of everything. So we examined the Camac-Mackendrick model and the SI model. So this also involved the epidemiological threshold of the Camac-Mackendrick model. Then determined and elaborated on the parameters of each model. We've seen what the infection and the recovery rates were, how we went about approximating those rates, and how we checked the accuracy of approximation with the chi-squared test. We also seen the variables of each model, S, I, and R. And then we compared the models to real-world data. So we've seen HIV modeled with SI model since it has no cure. And we've seen COVID-19 modeled with the Camac-Mackendrick model since recovered people were assumed to have permanent immunity. So if this research were to be continued, here are some potential directions that it could go. So we have test the chi-squared approximation method on other SIR models. So they could determine if this method approximates the rates of the other models as accurately as it did for the Camac-Mackendrick and the SI models. And then continue to evaluate the accuracy of the chi-squared method in Excel. So Excel has to continuously call on all of the solutions of the ODEs in the models since they are coupled. Therefore, there lies a possibility that other software can do this more accurately than Excel. So a good example of a software that most likely might be able to do it more accurately would be MATLAB. So if someone could implement this method into MATLAB, it may produce more accurate results. And also see if the models can be made accurate with small percentages, since I was unable to do that. Here are my acknowledgements, and here are my references. Are there any questions?
Great work, Chris. We do have a question from the audience, from Dr. McAdams. What was the most difficult aspect of your project, and how did you overcome it?
I think the most difficult aspect was finding a good approximation method for my rates, because I found about 1 or 2 other approximation methods, and then when I went to implement them into my models, they produced inaccurate results. So I was trying to determine a method that would produce the most accurate results that I could find.
Okay. From Dr. Walters, what did you use to solve the ODEs?
Oh, I used just Wolfram Alpha on the internet. So these models have no solutions when coupled together, but when you're solving them separately, they do have solutions. So I implemented that assumption, and then I used Wolfram Alpha to solve them separately.
And another question from Dr. Walters, how did you decouple them?
I mean, I just didn't refer to each one during the solutions. Not really too sure how to answer that differently.
Okay, other questions? Okay, I think that's all the questions coming in. So thank you very much, Chris. Clap, clap, clap. If you want to stop sharing your screen.
Let's see. Oh, there we go.
Okay, great. And I'll go ahead and shift over the co-hosting responsibilities to Connor.
Oh.
I know that we've increased our number of people in the room, which is great. I'll just remind everyone that they can enter their comments or rather questions for the conclusion of the presentations in the chat box, and we'll get those taken care of. And then also there's a Google form. The link is in the chat box as well. So feel free to log your comments on the different presentations. All right, Connor, I have that it's 1:30, so we'll let you get started.
Hey everyone, my name is Connor Waits and my project advisor's name was Dr. Marcus Wobish, and today I'm going to be talking about a novel method for computations of ratios of jet cross-sections in PQCD. And so here's an outline of what we're going to be talking about today. So moving into the introduction. This is a picture of the area surrounding the Large Hadron Collider at CERN, Switzerland. It is underground, and it runs underneath the border of France and Switzerland. Notice here, this is CMS and ATLAS. They're the two biggest experiments at CERN, and this is where the protons are actually being collided in this particle accelerator. All the data that we're looking at today was collected at particle accelerators. One data set was collected from the Large Hadron Collider. And it collides protons on protons at 13 TeV energy. Here's the ATLAS detector, just an example of one of the particle detectors that was used. So the proton beams enter from the left side and the right side and collide in the middle right here. And surrounding the collision center is a series of magnets and that track the path of the radiation, calorimeters that measure the energy, and they catch pretty much just about all radiation produced by the collision. And notice how massive this detector is. These are two humans for scale to scale to how big this thing is. So how are these particle jets produced? So we have two protons that are being collided against each other, and the protons are made up of 3 quarks each and are held together by gluons. And when they are collided at such high energies as these, then the quarks and gluons that make up the proton actually interact amongst themselves to form the collision. So here we have a diagram of a gluon-gluon collision that is producing a quark and anti-quark pair. We'll also see quark and anti-quark collisions, or quark-quark collisions in the proton to produce other quark-anti-quark pairs. And so when this quark is produced, it goes and travels through the detector and then further breaks down in a process called hadronization before it's finally detected into a calorimeter. And so the production rate at which certain processes happen can tell us about the cross-section, which is the kind of total probability for a certain process to happen. And so we calculate these cross-sections. So we have diagrams for a 3-jet and a 2-jet process. We call this a 3-jet process because the strong coupling constant, which is a parameter that characterizes the strength of the strong force, which is the force that's holding protons together and is the force of this interaction. And the strong coupling constant, alpha sub s, acts at this vertex, at this vertex, and at this vertex 3 times to produce 3 different jets that we detect. This is a 2-jet process because alpha sub s acts once here and once here to produce these 2 jets. So we measure, we calculate the cross-section experimentally by adding up the total number of processes that happen, or the total number of a certain type of process that happen over the total number of processes detected. But we get the theoretical predictive value for a cross-section by doing a perturbative expansion in alpha sub s. And so here are the perturbative expansions for the 2 and 3 jet cross sections. And we are just doing an infinite sum in alpha sub s, raising it to a power. And these coefficients are given to us by Parton distribution functions and S matrix elements. This sum converges because alpha sub s is much less than 1. And currently, we only have theory values for these perturbative expansions at next to leading order, so the first 2 terms. But because alpha sub s is about 0.11, that is usually a good approximation because it dies off fairly quickly, unless for some other reason these coefficients grow. And sometimes that does happen. So we also look at these, we can define ratios as well. And we look at ratios of these 2 cross sections because when there's a certain experimental uncertainties in a given cross section when you measure it, and when you take the ratio of 2 cross sections, then those experimental uncertainties simply cancel. And so we can combine the next to leading order and the leading order cross sections for a given process by using these K factors, which just gives you the next to leading order correction for the cross section. And it's often a nicer and easier way of looking at these. And so, like I said, we take the ratio of these cross sections, and the old way of taking these ratios that is normally used is to just take the simple ratio, take the perturbative expansion from one cross section and divide it by the perturbative expansion of the other cross section in the ratio. And here it is expressed in K factors. However, why not take the ratio of a perturbative expansion? To do this, we perform the Taylor expansion in the denominator of the ratio and in alpha sub s. And we regrouping terms, we get that these are the new coefficients for this ratio of perturbative expansions. And we can do this because the leading term of the 3-jet cross section is of order 3 in alpha sub s, and the leading term of the 2-jet cross section is of order 2. So when we divide them, they're of order, the 2 leading terms of orders 1 and 2 in alpha sub s. And now this, now this new method can be written in K factors like this. And so we can look at the difference between the 2 methods in terms of K factors. So now we're going to look at the old and new theory as compared to data for Atlas data sets and D0 data sets for different ratio measurements. So the first one we're looking at is Atlas measurement of R delta phi, just a different ratio measurement. And so we see that the old method is solid red and the new method is a dotted blue line. And our markers are indicating different choices of delta phi max. And our Y star is rapidity. And so this is for 3 different rapidity regions in the detector. We're measuring this as a function of energy. And so we can see that for the most part, our old theory and the new theory match up pretty well, which is what we should expect, because when the sums are taken to infinite terms, they should be exactly equal. So we're really just rearranging terms in this sum, but they might be different depending on how the momentum affects those K factors. And actually, one interesting thing is that our new method of calculating this ratio looks like it describes the data much better than the old method. And this rapidity region was actually excluded from the data set used to determine alpha sub s and when this paper was originally published, because the theory did not look like it fit the data very well, especially towards the end. If they had used this method, then maybe they might have found that it fit close enough and this could have been a useful addition to determining alpha sub s. Now we're moving to some D0 data, again for R delta phi. D0 was an experiment at the Fermilab Tevatron Collider, which is a smaller accelerator than the Large Hadron Collider. Actually, Louisiana Tech's physics department has 2 professors, Dr. Wobish and Dr. Sawyer, who worked on the D0 collaboration and are now a part of the Atlas collaboration at CERN. And again, pretty similar results for the differences between the old theory and the new theories, until we get out of here again. And the old theory wants to follow these two kind of outlying points. And these points have a lot of uncertainty in them, so we're not too sure about them to begin with. And it's a little worrying that the old theory wants to follow those points, but the new method really is very much in line with the data. I do want to say one thing about what the difference between the two methods gives us another kind of rough estimate of some theory uncertainty, because the difference is everything that we don't know yet. And so that's also another useful method of applying both of these theory methods. So here, measurement, we have very great alignment between the two theories in all choices. Now we're not looking at rapidity ranges, but we're specifying PT minimum values, and for different ranges of delta R. So there's not much to say about this plot. There's not a lot of theoretical uncertainty in these measurements, which is good, so we can be very confident about these predictions and how good our theory fits with this data. So here, worst agreement of all the measurements we looked at, and with the actually R32 measurement. So this is 3-jet cross-section over 2-jet cross-section, and there's a huge difference right here in the PT min equals 30 GeV. We looked at this to kind of figure out why, and the K2 factor, or the K3 factor, is very large in this ratio compared to the K2 factor. And if you remember, the correction for that, for the new method, was 1 plus K3 minus K2. And so that's a very big correction. And so is what's contributing here. But perturbative quantum chromodynamics also works much better at higher energy values. And so it's not really all that surprising that it's not a great fit right here. But as we see, when we increase the minimum energy requirement, we see much better agreement. And so in summary, today we introduced a new method for computing ratios of jet cross sections. To do that new method, instead of taking the ratio of a perturbative expansion, we instead take the expansion of a ratio. And this is useful to just kind of give another additional estimate of theory uncertainties, and as another test to ensure that the theory is actually in agreement with it, and we can really be sure of the quality of the data that we're looking at. Here are the references. So thank you for your attention. Are there any questions?
Great work, Connor. Thanks so much. Just a reminder to enter your questions over in the chat box. Anybody have anything for Connor today? Any questions for Connor? Why so much uncertainty in the last measurements? From Dr. Walters.
The last measure, okay. So I'm not entirely sure why there's so much uncertainty in all these measurements. Are you talking about the last measurements, like in the last part of the plot as a whole, or in this last graph?
Like in each plot, the last data point usually has a great deal.
Right, yeah, okay. So we're plotting all these against energy. And so as we get to higher energy ranges, our theory of, the detector introduces more uncertainty in those measurements than we do when we're measuring events at lower energies. And so that's why all the data points on the right side of the plots have much larger error bars.
Okay, thank you. So Dr. Walters commented, so it's a detector issue.
Yes.
Other questions for Connor? Actually, I think we're out of time. Connor, thanks. That was great. I'll let you go ahead and stop sharing your screen. And next up, we have Chen. Let me share the hosting with Chen. And Chen, feel free to go ahead and share your screen with us, please.
Okay.
Okay, great. We can see your slides and we'll let you go ahead and get started, Chen.
Okay.
You can go ahead and start.
Okay. Hello, everyone. My name is Shenshen Chen, and my project is forecasting daily stock market return with multiple linear regression, and my advisor is Dr. Zong. Yeah. The application of mathematical and statistical models are used to analyze finance and stock market is a universal and important field. The goal of this project is forecasting the daily value of S&P 500. The linear regression model is a very common and popular method in finance and business. So the data include S&P 500 index, ETF, and 11 financial and economical features in trading days from June 1st, 2013 to May 31st, 2018. So this project uses multiple linear regression to find the math model between the daily value of S&P 500 and 11 related financial and economical features. So the first is my Y, and the 11 financial and economic features are my X. So delta SPY is the value of S&P 500 in day T plus 1, and those 11 parameters are the value in the day T. This project will use those values of 11 parameters to forecast the value of S&P 500. So during the process of data collection, recording, or calculation, some data may be missing or exception. If analyzing the data without pre-processing, the result will be completely different from the expected data. Those processing data is an important step. So due to the data is huge, there are a lot of missing data in the correct data. So I will fill the missing data, and this project will choose spline method to fill the missing data. So, about the spline method, I'm going to find 3 data near the missing data. For example, you can see there is a 3 point. The first point is the value of the value in day T minus 1, and the second point is the value of day in day T plus 1, and the third point is the value of in day T plus 2, and the value of T in day T between this one and this one. So there are 2 cubical segments between these 3 points, and I need to find the 2 segments. So I'll find that the first segments in day t+1 must be equal, and the derivative it must be equal, and the second derivative must be equal. Then I can find the two segments. So I can use the segments I found to find the value of the value in day t. Oh, sorry. So there is sufficient flexible in the cubic spread procedure to ensure that the interpolator not only is continue differentiable on the intervalue, but also has a continuous second derivative. Since the data you removed this project is very large, so it may include some outliers. Therefore, clearing those outliers is an important step before data analysis. So this project will use quartile and the interquartile range to find those outliers. The width which cause outliers may be the extreme values or some error values due to the experiment in accuracy. So to detect the outliers in the whole data, this project will define an interval under the data which do not lie in the interval and are outliers. So quartile defines the data which are more than 1.5 in interquartile range above the upper quartiles or below the lower quartile as the outliers. So these two parts are outliers. So Q1 is the lower quartile and the Q3 is the upper quartile. So the interquartile is 1.5 times Q. The interquartile range is the Q3 minus Q1, and I need to find the 1.5 times the. I need to find the interquartile range is 1.5 times Q3 minus Q1. So after filling the missing data and the outliers, I can find the histogram of the after pre-process. As you can see that the first histogram is before pre-process, and the last one is the second one is the after pre-process. The whole, as you know, the horizontal axis of the histogram that after pre-processing is smaller, which present the data after pre-processing are more concentrated. Yeah, so the 12 histograms are all of after the pre-processing. So finish the pre-processing, I'm going to analyze data first. I need to split data. So in data mining, so when performing the predict analysis, the data generally divided into two parts, training data and testing data. So I'm going to choose the first 75% of data to be the training data and the last 25% of data to be the testing data. Training data is used to build the math model, and the testing data is used to test the math model. So when I finish express the data, I need to model selection. So because some independent variables have a significant linear regression with the dependent variable, and some independent variables are not significant. So the task of model selection is finding the simplest and the most effective model. So there are three kinds of model selection. First is forward, and the second is back, and the third is bidirectional. So the forward model selection is start with the model without any independent variable, then add the most significant independent variable into the model and repeat it until the no significant in the model. So back selection is start with the model has all independent variables, then remove the independent variable whose roots give the most insignificant, and repeat it until no independent variable can be removed and no insignificant. So bidirectional is combined of the above, the forward and backward. So it will run the ending or remove a independent variable to find the most simplest and the efficient model. So after those, I can get my final model. So my final model is just have the x1, x2, and x3 and x10. That's my final model. In the future, I'm going to use time series regression to analyze this project. Time series regression is a statistical method for predicting a future reprisal based on the response history and the transfer of dynamics from relevant predictor. Time series regression can help you understand and predict the behavior of dynamical system from experimental or observation data. Yeah, these are my reference.
Okay, thank you very much, Chen. Great job. Any questions for Chen? Just enter those over in the chat box. And as a reminder, here's the link for the Google form so you can log your feedback of the presentations. Any questions for Chen today? Chen, I'll ask a quick question. Before you started this project, did you know much about the stock market?
Stock market?
Uh-huh.
No.
So that was new for you?
Yeah.
Okay. From Dr. McAdams, how was the data divided into training and testing?
So I just choose the first 75%. So the 5% is from the June 1st, 2013 to the 75% of the day between my data and to be the training data, and the rest are my testing data.
Okay, thank you. Any other questions for Chen? Okay, I don't see any other questions for Chen, so thank you very much. We'll let you stop sharing your screen now.
Thank you.
And Chase, I have made you a co-host, so you can share your screen whenever you like.
Okay, can you hear me?
We can hear you just fine.
Perfect.
And we'll wait just a minute or so until 2 o'clock, and then we'll let you get started, okay?
Yes, ma'am. Text it.
All right, I think it's 2 o'clock, so feel free to go ahead and get started.
Okay, I'm ready. Okay, so my name is Chase Jones, and I did my senior capstone on the shallow water equations, and my project advisor was Dr. Dye. So today what we're going to talk about, we're going to introduce what the shallow water equations are. I'm going to give both algebraic and physical representations of what these equations look like. I'm going to show you the PDE that I focused on, called the St. Venance equation. I'm going to show you 2 initial boundary conditions, and then show you the several different groups and cases that I considered, ranging from cases 1A to 3A as well. And then we'll conclude. Okay, so for the intro, before I even get into this, the reason I got invested in the shallow water equations is because as a kid, I always loved meteorology, and I wanted to marry that passion with something mathematical. So in case you didn't know, Louisiana's coast is the fastest eroding in the world. Places like Ile de Jean Charles and Venice are eroding away as much as a football field of land a day. So I wanted to learn more about waves and coastal erosion to see how these things can impact our environment, because it's pretty local. So what are the shallow water equations? They're a set of hyperbolic partial differential equations that neglect surface tension, and they occur in hydrostatic balance. Another condition that must fit is that the distance from one crest of one wave to another must be greater than the distance from that crest to the seafloor. Usually these equations, we describe systems that are bounded above by some free surface and bounded below by some bottom floor topography. In any case, they can be used to describe ponds, creeks, rivers, and oceans. But specifically for me, since I was originally invested in oceans, we're going to talk about seafloors. These 3 equations here on the screen are the original shallow water equations. These equations are actually not the focal point of my research. I just wanted to introduce them because some of these variables are the same as they are represented in my St. Venance equation. To go ahead and define some of these variables are, the U and V components here, these are nothing more than the length and width components of the parcel of water. That parcel of water that I'm referring to, I'm going to show in the next slide. Just keep that in mind. And this N here is the free surface. In our case, the free surface is obviously the sea surface profile, so how the water is moving. This H is the seafloor topography, also known as the seabed. I'm going to use those interchangeably throughout the presentation. And G is our gravitational constant. And T is the arbitrary time constant we impose on our system. So to get a more physical representation of what I'm talking about here, what is a parcel? So here in this diagram, if you see this prism embedded, it's denoted C. This is a parcel of water. So this is what our area of interest, okay? So earlier in the intro, when I mentioned hydrostatic balance, what I'm saying is that every single particle flowing in this bed, this ocean, this riverbed, whatever this might be, has to be moving at the same celerity. So the velocity must be held at constant. Or on the different side of the coin, that water could also be stagnant, so there's no motion occurring. However, that's seemingly trivial in our case, so we won't consider water that is stagnant. Again, this U and V length and width components, this is the free surface denoted N. And this is the riverbed or seafloor, whatever system we're talking about, denoted H. And the distance from this surface to the floor is going to be, I'm going to refer to as the water depth layer, which you'll see in the next few slides. The equation that I focused on is this equation, which is the derivation of one of the St. Venance equations. There's 2 primary St. Venance equations, but this is the one that I'm focusing on in particular. I've also rewritten it in matrix form so we can see its results after coupling. To talk about exactly what is this stuff, this E sub A is a unit basis vector, and this D sub A is my dampening coefficient. Both, however, are represented as the identity matrix, part of I sub 2. The reason I kept them the same, I wanted to keep some kind of consistency so I wouldn't be changing multiple variables when I consider several different cases. Also, for the dampening coefficient, I was using COMSOL, which is a multi-physics package, to model these waves. And if I increased this matrix to be like maybe 2, 2 along the diagonal, you can see that the oscillation of the wave was no longer credible. So for here, and this partial derivative here, the U vector, originally that U vector was my dependent variable matrix. So it was a 1/2 denoted Z and V, which you can see here, where Z is the water depth layer and V is the velocity of the wave. But in order for this equation to work out nicely and put it in matrix form, I transposed that vector to be the 2/1 matrix, Z and V. And for this del term, this here, if you notice the dot product between del and gamma, this looks like some kind of divergence. And if you're thinking that, you're absolutely correct. This is a type of divergence. This is actually conservative flux. But the beauty of this St. Venus equation is that instead of having 3 dimensions that the original shallow water equations were considering, we've now reduced that to a single variable. And now we're taking the rate of change in the x direction, giving us this conservative flux. All of this is equal to our F term. This F vector here, it's a vector field, and it is 2 by 1 as well, and it's denoted as this matrix. This term here, we'll discuss a little bit later, and we'll try to break down exactly what that external force is. To find some of those variables, again, that Z, also known as Z naught, is that thickness of the water layer. So that distance from my free surface down to my riverbed, my ocean floor, whatever floor topography I'm talking about. V is the velocity of the wave, and I'm keeping everything here in meters per second just to have standard SI units throughout. The Z sub F term, that's the seabed profile, what that floor looks like. The Z sub S is my sea surface, and the Z also, CS could be written as the sum as the seafloor plus the initial water depth layer. And this is just a rearrangement of that expression or equation here. So the initial boundary conditions, for a long time during the project, I just thought there was one initial boundary condition. I thought the seafloor was the only thing I had to consider. And that's not true at all. So the ZF, again, is just what the bottom of this ocean looks like, the bottom of my aquatic system. And I kept the equation general, so for the sake of consistency when I consider several different cases. But I want to go ahead and lay out this equation algebraically. This A term gives me the amplitude of my sea ridge. So how high is my sea ridge? In every system that I consider, I've implemented a ridge, which is either a local or global extreme in my aquatic system, to show how a wave behaves after it passes over some ridge at some X location. So this is nothing more than the amplitude of that ridge. This X naught term is the location at which that local or global extrema occurs in the system, and the K1 is the linearization of the seabed. So the essentially the slope of the line before and after the sea ridge is implemented. The depth of the water layer, again, just the distance from the seafloor to the free surface, and I've kept this equation the exact same throughout in every single equation that I modeled in COMSOL. The only thing that will change is this 3 here. This 3 is actually should be denoted X naught, if you want to think about it like that, and I'm just going to change the location of the extrema here as well. Jumping into the cases, let's get some idea of what these actually look like. All of case 1, I'm considering when a wave is propagated at the location of the local extrema. So what does that mean? At x equals 3 here, we have some kind of sea ridge. You notice the linearization stops in this line. So I'm looking at a wave that's produced at x equals 3. And I'm going to model this wave over 20 seconds, 0, 10, and 20 respectively. So this is that wave at 0 seconds. This is the same wave at 10 seconds. Notice that the spin drift is now occurring, and the wavelength starts at the crest here is about 2, and the crest here is about 7, giving us a distance about 5. So let's keep that in mind, that wavelength was about 5 meters. And this is it at 20 seconds. And if you're wondering why I didn't continue maybe on to like a minute or so, one of the problems I ran into is that after 20 seconds, this no longer looks continuous nor differentiable. So I didn't think it was as credible to include those values after t equals 20. Now for case 2a, 1b, we are considering the same exact situation. Nothing has changed except I have multiplied the amplitude by 3 for my seafloor. Now it's 0.009 meters instead. So I wanted to see how the amplitude of the sea ridge affects the progression of the wave. So this is at 0 seconds. This is at 10 seconds. Again, though, notice that the crest here is about x equals 2 and the crest here is about x equals 7, giving us a wavelength of about 5 meters, which is about the same as it was for 10 seconds in case 1a. Those waves look very similar, which is going to be essential to understanding what's going on in this aquatic system. And this is at 20 seconds. And notice we have that same cuspiness that we saw in case 1a during 20 seconds. Moving on to case 2. Case 2, I'm now propagating my wave in the negative x direction or to the left of the sea ridge. Okay, so the sea ridge here occurs at 6, so I've just changed that location. And now I'm propagating the wave at x equals 2. So this is that wave at 0 seconds. There's that wave at 10 seconds. No, okay, notice here, this is the beauty of it. So since I propagated that wave to the left of the location of the extrema, notice how much shorter this wavelength is. I have a crest here about 3 and a crest here about maybe 6. So a distance of 3 meters. That's significantly less than when that wave was propagated at that same location of the sea ridge. Moving on to t equals 20, we get the same kind of cuspiness effect, losing some credibility here maybe. Case 2b, same exact scenario as before, except now again I've multiplied my amplitude by a factor of 3, giving me a much sharper sea ridge. So I wanted to increase some height here. Now, this is at 0 seconds, this is at 10 seconds, and this is at 20 seconds. So you can kind of see that progression over time. Again though, at 10 seconds, in case 2b, it looks a lot like case 2a at 10 seconds. Nearly the same shape of the wave, and the wavelength's nearly the same as well. Case 3a is actually it's more of like a lanyard section. So I wanted just to see, what does a wave look like when it goes into ascending water depth values? So you can see if this is our theoretical ocean floor, and notice, let me just point out, for each one of these diagrams, we are actually representing a physical aquatic system. So this is the sea floor, and this is actual height values. So what happens if I propagate a wave out here and it's moving into an increasing depth? So at 0 seconds, we have something that looks like this, and at 6 seconds, we have something like this, and at 14 seconds, we look like this. Notice how gentle and continuous and differentiable that curve is. It truly does not get better than that. That's just a little lanyard. So what does a wave look like when it gets deeper? It's a little more gentle. In conclusion, I learned a lot more than maybe I was anticipating. But I learned that our sea surface profile is only marginally dependent on the amplitude of our seafloor, or whatever our floor topography may look like, whether it's an ocean, river, creek, pond. But the sea surface is actually more highly dependent on the location of the local extrema of our seafloor, or the location at which the wave is propagated. For example, if a wave is propagated to the left of the sea ridge, then that wave is going to have a much shorter wavelength versus a wave that was propagated at the location of that mountainous region, that extrema. Models show that the spindrift, when it's propagated, also has about the same behavior. Like even if two waves are produced, and one is produced with a seafloor that is significantly larger than the other, those two waves have about the same behavior. And that's the reasoning behind why I'm saying the sea surface profile is only marginally dependent on the amplitude. And also, if I got to continue this a little bit further, something else I would do to benefit not only myself, but others to really grow, instead of considering just that one PDE, that St. Venance equation that I showed you that reduced the shallow water equations to a single variable in the x direction, what I would do is consider the original shallow water equations themselves and show how a three-dimensional system would behave, because that's more true to realistic problems that we have, especially in Louisiana. And these are my acknowledgements. Are there any questions?
Great work, Chase. Just a reminder, you can enter your questions over in the group chat. You can also find the link to the Google form there to log comments or ratings of the presentations you've seen today. Any questions for Chase? We have a minute before we need to switch over. From Dr. Walters, how difficult was it learning COMSOL?
How difficult was it learning COMSOL? Every day I felt as though I got increasingly more depressed. And I think that's because I was not used to COMSOL and no one else was used to COMSOL. So it was definitely a learning curve, but overall thankful.
Okay. Any other questions for Chase? Okay, hearing none, thank you very much. You can go ahead and stop sharing the screen. And Can will be next up, and I have made him a co-host. We're starting to get the hang of this now. So Can, sharing your screen. We're going to go ahead and let you get started.
Cool. Can you hear me?
Yes, we can hear you.
Okay, cool. Hello, everyone. My name is Ken Hong, and my project is the theory of cryptography in Bitcoin, and my project advisor is Dr. Dorio. So in my presentation, I'm going to discuss two components of cryptography of Bitcoin, hash functions and signatures, and I will describe what the hash functions and signature are. I'll give some examples of hash function and discuss certain criteria that good hash functions should satisfy. Now, first, what is a Bitcoin? So Bitcoin basically is a type of money that is completely virtual. Then what is a digital signature? So digital signature basically is a digital way to verify the identities. So if you want to create an account in the Bitcoin system, and you will receive a private key and public key. So the private key basically is a secret letters and numbers, and it's used to send your Bitcoin to another Bitcoin user. Then the public key is the cryptography code. It's allow the user to receive cryptocurrencies into their account. Now, what is hash function? Hash function basically is a function that shrink a long input into a short fixed size output. So why hash function is very important? So because, for example, if you want to rent a house and then you want to make a contract with your landlord, so you don't want anybody to change your contracts, right? So you can hash the contract to get a hash value. Then your landlord also can hash the contract to get another hash value. If you compare those two hash values, if they are the same, which means no one changed your file, then because it is very fast to find the difference between the it is very faster to find the difference using the short hash value than to find using its original value. So there are two properties of a hash function. The first one is collision resistant. So collision resistant basically means if you have two inputs, X and Y, but X is not equal to Y. So it is very hard to find the hash value h of X is equal to the h of Y. The second property is hiding. So hiding basically means if you have an input X, then you can hash it to get a hash value h of X. So it is very hard to go back, like from your hash value, go back to find your input X. So I list the four properties of a good hash function. The first one is efficiency computable. Basically means it should be very quick to evaluate the hash function. So the second one is hash function use all the input data. So basically it means the every bit of data from the input is used in determining the output. The third one is the hash function uniformly distribute the data across the entire set of possible hash value. So I will use an example to explain what the meaning of this property 3. The last one is the hash function generates very different hash value for similar input strings. So it means if you have two input, they're similar, but the output should be totally different. Now, let me use a very simple and very bad example. It's called reduction module 10. So reduction module 10, basically, just no matter what input we have, we only choose the last digit as a hash value. For example, so 1112, the last digit is 2. So, we choose 2 as a hash value. The second one is the same, 14,313. The last digit is 3. So we choose 3 as a digit, as a hash value. So, it does not use all the data because we can ignore all the input number except the last digit, right? So also, if we change the second digit to 2, I change it to 1112 to 1122. We know that hash value, it doesn't change, which means even I make a small change to the input, the output still doesn't change. So this is very bad. So, but this function does satisfy that Hodge function uniformly distribute the data across in the entire set of possible Hodge value. So because, for example, if we have input data from 1 to 100, we know 1 is output of reduction module 10, if and only if the input data are 1 and 11, 21, 31, 41, 51 to 91, right? We can easily calculate there are 10 different input data. We have 10 different inputs can generate the same output, which is 1. Similarly, there will be 10 different input data can generate output is 2, is 3, is 3, is 4, is 9. So therefore, they all appeared 10 times, which means the Hodge function uniformly distributes the data across the entire set of possible Hodge value. Now, the second example is Amplifier. Amplifier basically, it's a message digest. It takes the input of a message, then produce as a output a 128 bit. Now, there are 3 steps of the amplifier. The first one is the pending padding bit. The second one, the process each block. Then the third one is output. Let's look at the first step. So the first step we have to do is find the remainder of your message length divided by 512. For example, if your message length is 514, so you divide by 512, you will get a 1, and the remainder is 2. So the message right here is a remainder, so it should be 2 here. So if the remainder is not equal to the 448, we have the pending pad bits to let it equal to 448. So this part is the padding. Then after the first step, we go second step is the length of the original message module 2 to 64. So when we module 2 to 64, we will get a 64 bit here to get our plain text. So after those first step, we are going to the second step. It's called process each block. As I mentioned before, that every output amplifier should be 128 bit. So we have to break it to 4 parts. So each part is equal to 32 bit. Like here, A, B, C, D is all equal to 32 bits. Now, we can imagine that we are a cooker. So we want to cook a very delicious food, right? So all we need to do, we have to put all the sauces together. So mixing it. Here is the same thing. F is a function, it's a logical function. I will show you the next slide. It's a logical function mixing with B, C, D, right? Then you go next step, A goes down here, so you're mixing A, then you mixing with the MI is a plain text. We got it from the first step. Then I'm mixing with the KI. Then you can see you have A goes to B, B goes to C, C goes to D, D goes to A. Then the same thing, this is only the one step, one run of those process. All you need to do is just repeat those steps, and finally you will get 128 bits of the output. Here is amplify the functions. Now here is the hash value 75. Let's look at the first 2. So the first one, the input is 2. It's a very short input. The second one, well, it's longer than the first one. But we compare those to the output. We can see those output, they're the same size, but they're totally different. So here, which means no matter your input is shorter, it's a long, the output is always the same size. Now look at last 2 examples. We see I change the N to M here. So which means I make a small change of the input. So the output of the amplifier is totally different. So which means, well, even you make a small change of the input, so the output of the amplifier is to be totally different. Now, amplifier was a very good hash function, but it was broken recently. But it's not safe anymore, but it's still a very good hash function. Now there are SHA-2, it's much more stronger than the amplifier than it is in the Bitcoin system. It is pretty safe because no one breaking it now. So then I also use 4 properties to determine whether the hash function is good or not. I believe there should be a more specific way to determine the hash function is good or not. But I think my list of the 4 properties is the main part to determine the hash function is good or not. Okay, that's all. Thank you.
Okay, thank you, Can. Great job.
Thank you.
Any questions for Can? Just a reminder, you can enter those over in the chat window.
I see.
And we also have a Google form where you can provide your evaluation of each of the presentations you've seen.
Yeah, cool. Any questions? I didn't see.
Any questions for Can? So from Dr. Walters, can you explain more how this is used in Bitcoin?
How this to use in Bitcoin?
Yes.
Basically, in Bitcoin system, when you want to, for example, when you want to transfer some Bitcoin to another's, so you will have to use the signature, right? For example, signature. So when you transfer a Bitcoin to another's, so you have to use your private key to sign it, right? Then others, they can use your public key to verify the person is you. This is how the signatures that you use in the Bitcoin system.
So over in the chat, Dr. Walters has said, so you're using this for signatures.
Yes. Well, signatures is one part of the to use in the Bitcoin system. The hash function basically is like secure things to use in the Bitcoin system.
Okay. Other questions for Can today?
Cool. I think.
Okay. Yeah.
Thank you so much.
No more questions. Thank you. So we're about halfway through the presentations for the math capstone today. We do have a scheduled break at 2:30. So we will be back here together at 2:45 promptly for our next set of presentations. The Zoom room will stay open, so feel free to just join back again in about 15 minutes. Welcome back to the Math Capstone Zoom room. It looks like we are starting to get some of our presenters back. First up, we'll have Cassidy, and it looks like Cassidy's here. Cassidy, are you running your slides or am I running your slides today?
You are, if you don't mind.
Okay, I don't have your latest copy.
Just use the one that I uploaded on Moodle from Tuesday.
Okay, gotcha. Okay, can you see your slides okay?
Yes, ma'am.
Okay, we'll let you go ahead and get started. It's 2:45.
Okay. Hello, everybody. Thank you for stopping in to watch me present. My name is Cassidy Meadows, and my project advisor for this project was Dr. Brian Barron, and I decided to do my project throughout the year on the impact of eating and sleeping prior to testing. So just to recap, like what we're going to be talking about today in my presentation, I'm going to give y'all a outline of my project topic and the goal of that, and then some obstacles that I faced along the way. I'm also going to talk about how my data was collected. I collected it through a survey. I'm going to also talk about my test subjects that I used to collect this data and the amount of time I collected it in. I'm going to talk about what I did with that data and the calculations I made. And then also the results of the results of my project and the data, and then I'm going to conclude. So just kind of an update of my project topic. So I decided to do if eating and sleeping prior to testing has an impact on test scores, and I did this taking in the number of hours of sleep into account. So that was when there's tons of factors that I could have considered for this project. So I decided to do sleep because that was the most accurate considering all the possible ones and so I could actually get my hands on this factor other than like home life or, you know, background or something that they like, you know, if they stayed up all night studying for something, I actually had I could actually ask questions about their sleep. And then the goal of this project was to prove or disprove a said theory. So that theory was that I often heard before you go take a test, people will say, oh, eat a good meal, you know, before you go. And I was wondering, is that really true? Like if I eat before I test, is that really gonna, you know, how much better am I gonna do on that test? And then I also want to help students improve their math test scores in the classroom because that is an issue that we're having nationwide, is that math scores are just plummeting and we can't get a hold of it. So I wanted to see maybe if just through this, you know, simple test tip that we could maybe help students improve their scores. So some of the obstacles I faced when I was doing this project were that, like I said kind of before, factors to be considered. So I couldn't really given that I was doing this with the test subjects I was doing this with, I could not really go into I couldn't ask much detail basically. So I couldn't, you know, I really couldn't talk about their home life. I couldn't talk about the background that might, you know, affect their test scores. I couldn't, you know, if they have something personal going on, I couldn't really, you know, ask them questions about that and really gather data from that. So I had to think about and consider what factors can I use when I'm doing this project. And then also not being in the classroom. So I collected majority of my data over winter break, and we had a ton of breaks during winter. And so a lot of times I wasn't in the classroom to gather this data. And then also to ensure enough data was collected. So I had to, you know, kind of eye it and make sure, okay, do I have enough data to work with and to analyze and to draw results from? So how my data was collected, I decided to do a survey, and I gave it to, well, I'll get to that in a minute, my test subjects. I did a survey, and I asked them 2 questions. Did you eat breakfast this morning, and how many hours of sleep did you receive? So I gave this survey to high school students. I am student teaching at Neville High School. And so I was in, I had 12th graders, 10th graders, I had 11th graders, I had all of them. But I chose to do 12th grade students because they were my advanced math class and they were first and second period. So they were the very first periods of the day. And they were back to back. And the reason why I chose these 2 class periods was because I didn't want to choose classes to do this with after lunch, because my data would then kind of be, you know, a little skewed, because of course they're going to eat. You know, I'm going to have majority of them answer, yes, I did eat prior to taking my test. And then also I didn't want to do it like right before lunch or something, because that would give them, you know, more time throughout the day to, of course, eat. And so I kind of wanted to focus on eating breakfast before the test. So I then aim to do first and second period to do my study with. So the time span and the amount of data collected. So like I said, I collected my data throughout winter quarter. And how I did this was, like I said, winter quarter had a ton of breaks. So I was able to 5 different test days. They usually tested on a Friday. So 5 different Fridays, I was able to pass out the survey to my students before they took the test and collect the surveys back. And I did this with first and second period. So total, I had 10 final statistical calculations that I used to draw conclusions from. So a little bit about my data. You're probably thinking, why did she choose? I gave the survey out on paper. And the reason why I did this was because I wanted to give it before the test. So that way, it's less distracting. I go ahead and get it out of the way, then they can focus on their test. Also, if I did it through like electronics, if I decided, hey, let's give this survey through, their cell phone or something, then I would have to ask them to have their cell phones out before the test, and that's not really a good idea because, you might not get them back. And so I stayed away from cell phones. And then also I wanted to separate my results, the survey from the test, because my mentor teacher kept the test. And then also I didn't want to forget I didn't want them to forget to answer the survey questions. So I was there to hand it out and I collected it immediately. And I was scared that if I put it on the back of the test or something, that they wouldn't get around to it. And then organizing this data, I separated my data because I did have a lot of it, given that it was on paper. I had 30 students in each class. So I had 60 students total for each test day. So that's a lot of tests or a lot of surveys to keep up with. So I separated into test days. So I had 5 different stacks for 5 different tests. And then within each stack, I separated it into class periods as well. So here's just a picture of my completed Excel charts for each test taken. And I had 5 different sheets on Excel. So I did one for each test day, but I only included 3 here just so y'all can get an idea of how I organized it on Excel. And what I did was I took a lot of averages at first. I did more calculations, but at first I just wanted to just get a visual idea of what my results looked like. So I took the averages of the total average yeses and the total average no's. So the average score of the students who answered yes, they did eat, and then no, they did not. And I did this for each period within each test. And then also I averaged out according to sleep what they answered for that. So when it came down to sleep on my survey, I had them just check boxes. And I had the option 0 to 2 hours, 2 to 4, 4 to 6, 6 to 8, and then 8 to 10, 10 plus. So they had lots of different options to choose from. So therefore I had, a good bit of categories within my data. And so I averaged out each test score among the yeses according to what they chose, and then the no's according to what they chose in regards to how many hours of sleep they received. So some other calculations that I did, aside from the averages, my main goal was to determine the statistical significance of my data. And so in order to do this, I had to kind of work backwards. So I first had to, I had to do a z-test, but in order to do a z-test, I had to have the standard deviations of them. So I took the standard deviations using this formula, and I used that standard deviation to put it into my z-score test. And the z-score test that I used, because there are different ones, I used 2 means with known population standard deviations. And I did this z-test because the 2 means I used were the mean of the yeses and the mean of the no's. And so I had 2 means, so therefore I would use, this z-score test. And I did this for each and every class period within that test day. So test 1, I did a z-score test for first period and second period. For test 2, I did a z-score test for first period, second period, and so on. I found that this was the best way to do it because I did have so many different categories and just broken up into so many different, considering sleep, considering, how many hours of sleep, considering if they ate or not, all these, two different class periods. And so this was the best way I found to do it. And then when I did the Z-score test, I used a significance level of 0.05, and this says that there's a 5% chance the results occurred at random. I use this one because I really had to do like research on it, because I've only had one stat class really in college, but I had to do research because I was like, well, I don't know which alpha to choose, and so I chose this one because it is the most common to choose, and yeah, it's the most common one to choose. So that's why I chose it. And then I'll kind of tell you a little bit of what it means in a second. So this is a table of the Z-score test and the p-value. So once I got the Z-score test, I was able to get a p-value from that. And all I did there was just look at the p-value chart to get my p-value. And really, when I did this, I was looking at my p-value. That's really was like the indicator of the statistical significance of my data. And so if my p-value was less than my significance level that I chose, then it did have statistical significance. And the key about this was that I was sure to pick my significance level before I did any of my calculations or any of my data and stuff, because one could easily just pick a significance level after you get all your p-values and be like, oh, looky there, it all has statistical significance. So I was sure genuinely to pick my significance level beforehand, so that I could have genuine results. And so as you can see here, first, the test number 1, 2, and 3, if you look at their p-values, they are greater than the significance level I chose. So therefore, first, second, and third test scores did not have any statistical significance, meaning that the impact, like eating and sleeping, did not have an impact on their test scores. But if you look at 4 and 5, test number 4 and 5, if you look at their p-values, they are less than the statistical level that I chose, which was 0.05, meaning that those two tests, the data that I was able to extract from those two, they did in fact have a statistical significance, meaning that if they ate or slept, if they got an adequate amount of sleep, and if they ate prior to the test, it did have an impact on a positive test score. So in conclusion, looking at the third bullet here, I wanted to point out that this is evidence for correlation, not causation, meaning, and this is due to a small sample size. So my sample size, I had about 30 students probably in each class period. And so what I'm trying to say is that this observation, this project that I did, I got about halfway through and I realized, oh my gosh, my results may not be all great and dandy like I wanted them to be. Like I thought that I was just going to come out at the end and be like, looky here, if you eat and you sleep, like you're going to get 100 on the test. Like, and I had to realize real quick, Dr. Evans was like, no, you are, getting data, you are observing. Your data is not always going to be perfect. And I was like, okay, you're right. And so that's exactly what I had to realize, is that I'm showing the correlation between students eating and getting an adequate amount of sleep prior to testing and scoring well on tests, but not that these factors alone are how to score well. So, and I say this because, like I mentioned beforehand at the beginning, there are other factors in students' lives that I can't go there. And so it's really hard to consider other factors. Now, if I were to be able to consider all different kinds of factors, it would be a lot more, accurate and more, less correlation and more like, yes, this is definitely how to score well, is by doing these two things. So I just wanted to point that out. It was really fun doing. My students were like, what are you doing, Miss Meadows? And I was like, well, and I did inform them of like what I was doing and stuff. I got permissions. And so, but yes, I did want to point that out, is that there was a correlation between 2 of the test days, but 3 of the test days showed no statistical significance. So, and that is it. Is there any questions?
Okay, thank you, Cassidy. Just a reminder of, okay, we do have a question over here. How do you think your data would have turned out with a larger sample size?
If I had a larger sample size, I think that my data would have probably been a little bit more, I don't want to say accurate. It would have probably been, even though there's more people, it would have probably been more accurate, honestly. I was able to, and I know that would probably be a huge handful of, data sets and, papers to keep up with. But I do think that with more students to take the survey, I would probably have a better idea of statistical significance, and I would probably, it would probably have a bigger impact, and it would probably say a lot more than my, 30 students I had for each Z-score test.
Okay, thank you, Cassidy. We are going to go ahead and turn it over to Luke Seaton for the 3 o'clock presentation. I apologize, we couldn't get to all those questions. Just a reminder, while Luke is...
I think I had another question. I think I had more from Dr. McAdams. She said, how to continue the research.
Right.
I would say that, which I put this in my final paper, but you could, if somebody did further research on this and they did find like, hey, this is helping students score better, we could implement breakfasts in schools, because I know some schools don't have a breakfast program, and some do. And so if it showed positive results, you could say, hey, let's implement breakfast before students, test or something on test days, or even just throughout the week, and help them to do better. And you could even help them not just in math. I did mine with a math class, but you could help them, whatever test they're doing. But if you could implement a breakfast program, that would be a good idea.
Okay, thanks, Cassidy.
You're welcome.
All right, Luke's got his screen up. So Luke, please go ahead and get started.
Okay, thank you everyone for stopping in to see this. This past year, I worked with Dr. Doyle and got to dive into some number theory and specifically dynamics. So today I'm going to give an introduction to kind of what the field of dynamics is, and then go into some background and then a motivating question that kind of set me off on part of the research that I really got into. And then I'll have some pretty graphs to look at because everyone likes pretty pictures. So a dynamical system represents how the state of a system changes over time. This change can be captured as ongoing time or an interval, so continuous or discrete. So a continuous system would be modeled through calculus and differential equations, while a discrete model could involve iterative mappings where the output of a previous state is used as the input for the next iteration. So we've actually seen some examples of dynamical systems already today. If you've tuned into Chase's presentation where he talked about some like shallow water wave equations, and Chris talking about the spread of COVID-19. So to introduce some notation, we're going to write the composition of f with itself in times as like a superscript. So this represents in iterations of the function f. And we're also going to define a periodic point. So a point P is a periodic point of a function f with period m, where m is the smallest integer satisfying this equation here. So that means like if you were going to make a sequence of the iterations and you start with P, when you iterated m times, you would eventually come back to P. So for example, to see what a periodic point looks like, we can consider the function x squared minus 1. So if we evaluate at 0, we can see that we have f of 0 is a -1, and then we evaluate at -1, and we get 0, and then 0 to -1, -1 to 0. So they're kind of just flipping back and forth. So we can see that both 0 and -1 are periodic points, and these points are points of period 2, because if we iterate if we start with 0 and iterate twice, we get back to 0. If we start with -1 and we iterate twice, and we get back to -1. So to frame the question, now that we introduced periodic points, to frame the question, I want to ask, like, how many periodic points can a function have? And as a good starting place, we're going to ask, how many periodic points can a polynomial have? So when we look at the number of rational periodic points, we can see that that has been shown to be finite by Northcott in 1949. And complex, we also see there's always an infinite number of periodic points. But when you look at the real number of real periodic points, it can be either finite or infinite. And that was interesting to me. So I actually looked into Sharkovsky's work, and he kind of tackles the real periodic points. So we are going to assume the polynomials we're looking at have degree greater than or equal to 2, because degrees 0 or 1 are going to act differently. So to introduce Sharkovsky, this theorem uses an ordering of the natural numbers that you can see here. We're going to read that triangle symbol as left of, so you'd say like 3 is left of 5. And this ordering is, I have the second line here so you can see a little more clearly how they're actually grouped together. So you have the odd numbers, and then 2 times the odd numbers, and then 4 times the odd numbers, 8 times the odd numbers, and that continues until you get, then you have at the very end, you have the decreasing powers of 2, and you end with 1, which is 2 to the 0th power. So Sharkovsky's theorem says that if you have a continuous function, you can suppose f has a point of period m, and if m is left of n, then the function also has a point of period n. So for example, if we have a function of, if you have a function that has a point of period 5, we can also say that by Sharkovsky's theorem, that the function also has a point of period 7. So what we see would be really interesting is if we could find a function with a point of period 3, because a point of period 3 would have points of periods of all of these other natural numbers. So through, so I actually happened to find a really cool function. So we're going to call it officially here. And so if we evaluate at 1, we see that the answer is 2. And if you don't want to do the fraction math, you just have to trust me on this one. Then we can evaluate at 2, and the answer is 3. And we evaluate at 3, the answer is 1. And you can see we would evaluate at 1 again, and we get stuck in this cycle where we'd have 1, 2, 3, 1, 2, 3. So we can actually say that 1 is a point of period 3. Similarly, we can also say that 2 is a point of period 3, and 3 is a point of period 3. So if we look back at Sharkovsky's ordering here, we see that 3 is at the very beginning of this ordering, meaning that Sharkovsky's theorem says that this function has a point of period n for every n in the natural numbers. So this kind of brought me to like a motivating question. So if we're looking at a polynomial function of degree greater than or equal to 2, and we see that it has points of period 3, can we find an interval that we can kind of that satisfies these 3 conditions? So we're looking at this function. We could use this function as an example, and we want to see if we can shrink down the interval so that it no longer has points of period 3, but it does have points of period 5. And so a simple counterexample of this is considering the critical point. So now we're going to look at some of these graphs that will more clearly show this, and how the critical point is actually a very interesting part of these systems. So right here we have the function, which is the same function we were using that for our cool function from earlier. This is our cool function, and it is graphed against the line y equals x. So when you graph a function against y equals x, you can actually see the points of period 1. So we can see, I don't know if you can see my mouse. Can you guys see the mouse? Okay, awesome. So this would be a point of period 1, this would be a point of period 1, also called fixed points. So if we look, we can also graph the third iteration. We can draw like F3, and we can actually see the points that we were talking about earlier. So we have 1, 2, and 3. And there, you can see that there are also some other points on here, but trust me, you do not want to see them written out because they are not rational and they would take up more than a screen wide of numbers. They're not very pretty to look at, but this function does have like these 3 rational points of period 3, and you can clearly see them on here. So now if we look at the second iteration of f, and I've actually added these lines, a purple line up here and a black line down here. This line right here is the output that we get from when we plug in our critical point here. And if we look at the critical points of F2 now, we can actually find that this line down here is like the second iteration of the critical point. So I thought that was interesting. So I went and looked at the 4th iteration, and I actually a few more, but the pictures get kind of messy. As you can see, the 4th iteration here, you already have kind of a messy picture, but you can still see that it bounces off the top here and bounces off of this bottom here. And if you actually look at the, if you look at more iterations of the critical point, you get the lines here and here as well. So that's where this project is heading for the future. And I have my bibliography. Are there any questions?
Okay, great, Luke. Thank you. Just a reminder to the audience to put your questions over in the Zoom chat. And there's also a Google form that you can use to evaluate each of the presentations you see. The link for that is also in the Zoom chat. Any questions for Luke today? So from Dr. Walters, can you ever guarantee rational points?
I think there's also a question from Dr. Turner.
Oh, okay.
Okay.
Didn't see that, Dr. Turner.
Okay, so for Dr. Turner's question, I found the function through, I was reading through literature. I read through quite a few dynamics papers, and I saw someone use that function as an example, and I thought I could take that example further. Can you ever guarantee rational points? I don't think so, because I don't want to say anything wrong, so I'm going to end with I don't think so.
Other questions for Luke? Okay, well, thank you very much, Luke. Next, Chelsea will be presenting on fantasy football. And I've made you the co-host, so you now should be able to share your screen. Okay, great. We can see your slides. We'll hold off just a minute, and that'll get us to 3:15.
You ready?
Okay, let's go.
Okay. Hi everyone, my name is Chelsea Robinson, and my advisor was Mr. Stan McCaw, and I did my project on the prediction of fantasy football. So today we're going to talk about a little background of fantasy football. What is it? How does it work? the scoring system that I use to calculate the points. We're going to talk about my models. I used the Arima model, and I just made an algebraic expression to add up the offensive players' points. Then we're going to talk about some of the results I got and the conclusion and future work. So the goal of my project was to develop a quantitative method of ranking players for the fantasy draft. So I used the Arima model to predict players' performance. And with this Arima model, I predicted the 2020 fantasy football draft. This project was a little personal for me because my dad plays fantasy football, and I was able to help him with the next year draft. So fantasy football is a game in which people choose real players to form an imaginary team and win points every week based on actual performances. This is basically the process of fantasy football. First, you join a league. It could be a public league or a private league. You could play for fun. You could play for money. It's whatever you consider or whatever you want to do. Second, you prepare for the league by drafting and scouting players. This is the most important part. This is the part that I did. You research players, you research their stats, and you pre-rank players for the draft. So when the draft comes, you'll know which player is predicted to do the best for that season. Next, you build your fantasy football team via draft. You could do a snake draft or an auction draft. You could pull, if you're playing for fun, you could pull names out of a hat, anything. And the fourth thing you do, your team competes each week against one another, and you calculate your points each week based upon the player's actual performance. And then the next thing, you can make moves to improve your team every week. So basically, this could be if a player gets hurt and can't perform the next week, or if you predict that your player might perform better against this team, you just switch out players. And the team with the most points win at the end of the season. So this is the Ppr scoring system. It is the points per reception. I use this one because it's basically the same thing as a standard scoring system, but it adds an extra point for each reception a player gets. So you can earn extra points using this scoring system compared to a standard scoring system. So this is my model. I use the Arima model. Arima is an acronym that stands for Auto-Regression Integrated Moving Average. The Arima model is used for analyzing and forecasting time series data. So the AR part of the Arima model stands for auto-regression, and that means that it's the dependent relationship between an observation and some number of lag values. The I part is for integrated. It is the differencing of the raw observation. And the MA part is the moving average. This is the dependency between an observation and an error from a moving average model applied to a lag observation. And you combine these two equations together. The mu is the constant. The alpha is the coefficient of the auto-regression parameters. The beta is the coefficient of the errors. And the T subscript T part is the errors, and the Y subscript T is the variable that will be explained at T, and T is the time. My second model is a model that I made. It was just a model to be able to add up the fantasy football scores for each offensive player. It'll be an easier way than going through and just, if y'all seen on my last slide, it's like every 25 yards you earn a point. And I'd rather just do it in a way that I could just plug in numbers in Excel and keep on going, because it was a lot of data to deal with. And as you can see, the quarterbacks, the only matters to add up a quarterback fantasy score is their passing yards, their interception, their fumbles. The PPR scoring system gives running backs, wide receiver, and tight ends a better chance than quarterbacks. It just helped, like, running backs and wide receivers are to be predicted to make the most fantasy points using that system. So this is some raw data that I use. This is an example of what I did in Excel. I had to do this for every player of the historical stats. So I use Lamar Jackson because he is predicted to have the most fantasy scores of the best quarterback, even though he's only played in 2 seasons. And I predicted the rest of his season based upon this data all the way into his 41st game. And basically you did the games per the passing components, the games per passing attempts, the games through the passing yards, and the games per passing touchdowns. And when you did that, you had to use the forecasting, and it did it all by itself. And he's predicted to have 419 points for the next season. And this graph, the first graph shows his historical points, and then it shows the forecast of how many touchdowns he's predicted to make in the next season. And an average of 70.16, that's how many passing touchdowns he's predicted to make. And I also show the graph is how many interceptions he's predicted to throw. And it's basically kind of like 0, 1, back and forth. This is how I rank the players. I rank players based upon their fantasy scores. As y'all can see, a running back is predicted to make the most scoring points for the next season. And basically, I have 11 running backs already in the top 20 that is predicted to make the most scoring points for the fantasy football. Lamar Jackson is predicted number 19 as the first quarterback to be drafted. And this is basically just ranks of how the players will be drafted. And for my conclusion, I did the absolute, the mean absolute percentage error to check the accuracy of the 2020 to check and predict the fantasy scores. The method was we're using to repeat all data for each player until 2018 instead of 2019, predicting the fantasy score for 2019, excluding the first-year players. The absolute percentage error between the 2019 forecast and the actual was derived for each player. The mean absolute percent error was average, and I came out with 4.65%. And this is kind of like good data because the model didn't exclude for players' injury, and you never know when the players to get injured. And the Y is the actual value, the Y subscript T is the forecast value, and the N is the number of observations. And for future work, I plan to predict the defense performance. I tried to do some defense data, and I was getting a whole bunch of negative points because I kind of didn't understand how would I rank the players and how is they to be drafted when sometimes defense players don't make as many stats as others, the offense players. And I wanted to research more about how injuries hurt fantasy scores throughout the season. And just say your player is injured and you predict you draft 3 players that get injured. Could you trade out, or would it be fair if you trade out players and things like that? And is there any questions?
Okay, great, thank you. Just log your questions over in the Zoom chat. From Dr. McAdams, did you compare your model to any other models?
I looked for some models that were listed, and no one really have an accurate model of how to predict players. Some fantasy football players, they really just do all raw data, like just stats and things like that. But I never seen no one use the Arima model.
Okay. Other questions? Did you run the Arima model in Excel or in some other software package?
I ran it in Excel, but you can do programming with it, which it seemed a little difficult because you had to know like values of P, D, and Q. And it's basically the same thing. The P was the lag values, the I was the differencing, and the Q was the differencing of the movement average.
Okay. And we do have a funny comment from Dr. Walters. I think he's working on his retirement. And from Mr. McCall, will your dad give you credit if he wins?
I hope so. I did a lot of work to get. I would hope so.
Yeah. Okay, well, thanks so much. You can go ahead and stop sharing your screen. And next up, we have Brian. Okay, so Brian, I'm making you the co-host. You should have the ability to show your screen. And we'll wait just a few minutes and begin your presentation at 3:30. In the meantime, you all can log your evaluations over on the Google form. Okay, Brian, I think it's 3:30, so we'll let you go ahead and get started.
All right, good afternoon, everyone. I'm Brian McCormick, and my presentation is on the axiom of choice and some related topics. and my project advisor was Dr. Doyle. I'm going to start off by giving a brief introduction on the history of set theory, followed by some discussions on the axiom of choice, Zorn's lemma, and the well-ordering theorem. So set theory is a branch of mathematics that studies collections of objects known as sets. And prior to the 1870s, it had no strict defining axioms, and it was kind of just defined by word of mouth. It was just spread by what seemed logically right. But this definition of set theory resulted in paradoxes, notably Russell's paradox. Russell's paradox just states, consider the set of all sets that are not members of themselves. If that set is a member of itself, then by definition it's not, and vice versa. So that was one of the paradoxes that were in naive set theory. So in the 1870s, mathematician George Cantor, he began to try to formalize set theory, get some strict, rigid definitions and axioms. And Ernst Zermelo and Abraham Frankel tried to build on what Cantor had started. So they came up with the Zermelo-Frankel axioms, and they form the basis of modern set theory. There are 8 axioms that they came up with, and they accomplished Cantor's goal of creating a strict definition of set theory that didn't have any harmful paradoxes. However, Zermelo, he wasn't satisfied with just these 8. There was another axiom that he wanted to include. And that axiom was the axiom of choice. It's the 9th axiom of ZF set theory. ZF just stands for Zermelo-Frankel. And it states that given any number of mutually disjoint non-empty sets, you can make a set containing exactly one element from each of the sets in the collection. It pretty much means that, if you're given a bunch of sets, you can just choose one element from each of those sets. You don't have to, there doesn't have to be a strict definition. It just states a choice function exists. You can just choose one. And this axiom, it allowed Zermelo to prove some theorems that he couldn't prove with the original 8 axioms, but he thought that the theorems were true. The only problem is that acceptance of the axiom of choice resulted in some paradoxes, which was kind of the purpose of formalizing set theory so that we wouldn't have paradoxes. The most notable paradox that results from the axiom of choice is the Banach-Tarski paradox. The Banach-Tarski paradox, it starts by taking a sphere in 3-dimensional space and decomposing it into finite sets of points. And some certain rotations and translations are defined. The proof is pretty rigorous and complicated, but they take these points, they rotate them, they translate them, and you can use the axiom of choice to reassemble these sets of points and get 2 identical copies of the original sphere, which, it goes against all logic. It goes against, the basic rules of geometry and stuff. It just doesn't make sense. But mathematically, it was true. However, these sets that they're working with, it turns out that they're non-measurable sets. The spheres have no volume. So while it is mathematically true that this is possible, it doesn't really have any negative real-world consequences, but it is a mathematical paradox that results from the axiom of choice. I'm now going to shift over to Zorn's lemma. Before I discuss Zorn's lemma, it's important to define a few terms in order theory. A partial order, it's a way to order elements of sets when you can't necessarily compare each element of the set with every other element. An example that really helped me understand partial ordering is if you consider a family tree and you consider the relation of like a descendant. So in a family tree, a child is a descendant of their parent. You can compare them that way. But if you take a child and their cousin, you can't really compare them. One's not greater than the other. You just really can't compare them. That's an example of a partial order. A total order, it's a way to order elements of sets when every element of the set can be compared to every other element. So for example, the real numbers. Every real number is less than or greater than or equal to every other real number. And a well order, it's similar to a total order, but in sets with well orders, every subset has a least element, like the natural numbers. Any subset of natural numbers always has a least element. And a chain, it's just a totally ordered subset of a partially ordered set. This leads us to Zorn's lemma. Zorn's lemma states that if every chain in a partially ordered set has an upper bound, then there is a maximal element of the set. Here, maximal doesn't necessarily mean it's the greatest element. It doesn't mean that it's greater than every element in the set. It just means that there's no element of the set by the partial order that is greater than that element. So you could have multiple maximal elements. You could just have just one, but it's good to know that it's not necessarily the greatest element in the set. And Zorn's lemma, it's a very useful theorem. It's called Zorn's lemma, even though it's more of a theorem. It's just kind of a historical quirk, but it's used to prove many other theorems across different fields of mathematics. One of these theorems is Krause Theorem in abstract algebra. It's proven using Zorn's lemma, and it states that every non-zero ring has a maximal ideal. An ideal, it's just a special subgroup of a ring that satisfies certain multiplicative properties. An example of an ideal in the integers is the even numbers, because you can take any integer, multiply it by any even number, and get an even number as a result. So the even numbers form an ideal in the integers. And Krause theorem just states that every non-zero ring has a maximal ideal. And coincidentally, Krause theorem, it's actually equivalent to Zorn's lemma, meaning you can use Krause theorem to prove Zorn's lemma. You can use Zorn's lemma to prove Krause theorem. Now I'm going to shift to the well-ordering theorem. The well-ordering theorem was Zermelo's primary motivation for creating the axiom of choice. It states that every set has a well order. Now, this seems like it shouldn't necessarily be true. I mean, consider the interval 0, 1 in the open interval 0, 1 in the real numbers. If the real numbers have a well order on them, then that interval should have a least element. But that's not true by our normal definition of less than. But the well ordering theorem just states that a well ordering exists for every set. It doesn't necessarily have to be a defined well order, just that it exists. And the primary consequence of the well ordering theorem uses ordinal numbers. And you're probably familiar with ordinal numbers a little bit. Ordinal numbers, they just describe the order of elements in a sequence. For finite sequences, it's the same as the cardinal numbers, first, second, and third. It's the same as 1, 2, 3, and so on. But when you get to infinite sequences, orders get a little weird. You have to define these new type of ordinal numbers called limit ordinals. And the first limit ordinal is omega, and it's equivalent to the order of the natural numbers. And we use ordinal numbers in transfinite induction. Transfinite induction is the primary consequence that I've found of the well ordering theorem. It's the most used that I found, and it's that it can be used with any infinite set. Transfinite induction, it's similar to the typical mathematical induction that you use in your first proof class of mathematics. The only main difference is that you have an extra induction step for limit ordinals. And the way the transfinite induction works is you pair your elements of the set to the ordinal numbers, and that allows you to do transfinite induction. This is very useful proof technique. So in conclusion, you might be wondering, these theorems and lemmas and axioms, they seem kind of unrelated. How do they all come together? Well, it turns out that the axiom of choice, Zorn's lemma, and the well-ordering theorem, they're all equivalent statements. This means that by using the ZF axioms of set theory and one of these statements, you can prove the other two. And these axioms, lemmas, theorems, they all have many more consequences, equivalent statements across many fields of mathematics. For example, there's many uses in abstract algebra, functional analysis, topology. Without accepting the axiom of choice, modern mathematics would be radically different today. So because of that, most people tend to look past the few paradoxes like the Banach-Tarski paradox and accept the axiom because of how useful it is. Does anyone have any questions?
Thank you, Brian. From Dr. McAdams, what is your favorite paradox?
My favorite is the Banach-Tarski paradox. It's actually what motivated me to start this research. I stumbled across a video talking about it, and I thought this is really cool, how it's true mathematically, but it just doesn't seem to make sense. And that's what got me interested in kind of digging down into the math that allowed it to be true.
Okay, other questions? From Dr. Walters, do you mean without the axiom of choice by meaning assuming it's false?
Yeah, so there was a really big debate when the axiom of choice was first introduced by Zermelo. Many mathematicians of the time thought that it should be false because it results in these paradoxes. So people shouldn't accept it to be true. They should assume that it's false. But most mathematicians today realize how useful it is and they assume it to be true.
Okay. Other questions for Brian? Another one from Dr. Walters. So you mean it would be different by the fact we wouldn't have certain results, or do you mean something else?
Exactly. Without the axiom of choice, many, like some of the theorems that some of the consequences of these theorems I introduced in this paper, others like in abstract algebra, every vector space has a basis. That proof relies on Zorn's lemma, which relies on the axiom of choice. So without accepting the axiom of choice as true, we either would not have proved those theorems, or we would have had to come up with some other way to prove those theorems, which might have taken longer. They might have been discovered much later than when they actually were.
Okay. Any other questions for Brian?
Yeah, actually, there is a the book is titled "The P in the Sun" because there's another form of the paradox that says you can take a sphere, for example, the size of P, and rearrange it to be the size of the sun. So it's kind of like another wording of the paradox, but it uses the same results.
Okay.
All right. Thank you, everyone.
All right. Thanks, Brian. So coming up on 3:45, next we'll have Callie talking about Sudokus. And Callie, I've made you a co-host, so you should be able to share your screen. Okay, I think it's 3:45 if you want to go ahead and get started, Callie.
Okay. My name is Callie Weaver, and my project advisor was Dr. Stacey McAdams, and we were discussing the game theory of Sudoku. Here's a brief outline of what I'm going to talk about today. It goes over the introduction, some models of Sudoku, strategies, algorithms, and theorems. Also, while talking about how Sudoku in education can be used as a tool, and some conclusions. So to start, game theory is the branch of mathematics concerned with the analysis of strategy for dealing with competitive situations when an outcome of a player's choice of action depends on another player's choice of action. And to explain a little about Sudoku, what is it and some terminology. Sudoku is a puzzle in which players insert the digits 1 through 9, or actually a variety of any 9 symbols, into a grid consisting of 9 squares, further divided into a grid of 9 squares, in a way that every number appears once in each horizontal line, vertical line, and block. So some terminology, the little squares right here is called squares. The 3 by 3 small is called a block. A candidate is basically a possibility of whichever digit could go there. A row is obviously a horizontal line, a column, vertical line. A virtual line is any of these lines so that we know that the digits 1 through 9 must be in those blocks 1 through 9. And then a buddy is any, instead of it being a line, it will be the numbers in that block with it. So the questions of the project that I wanted to address were, are there patterns present in a puzzle? And can you use those patterns to model or form a Sudoku puzzle? Also, what strategies and algorithms are there? And how can Sudoku be an educational tool? So with the permutation matrices, this is just an example. It's actually a little bit of a wrong size, but when you focus on just the 3 by 3, you see that we can give 1s to the given position and 0s as every other digit. However, as you take 1 away from those every time and add a new digit, it will create a Sudoku puzzle. But by using permutation matrices, you can see how the puzzle is set up and formed, especially when you're trying to teach a new player how to solve a Sudoku puzzle. It's easier for them to solve one once they understand how it is formed. It basically gives a visualization. And it also can become a strategy for any size Sudoku rather than just the normal 3 by 3. It can be used as a 6 by 6, a 3 by 2, etc. The rows and columns are represented by little n, and the blocks in a row or column are n. Like a normal one, we would say is a 3 by 3. And by using the steps to create the permutation matrix example, you can use that as an algorithm. You can also model Sudoku puzzles by symmetries using the bands and stacks and the axis of symmetries. The rows of the 3 blocks are called bands, and the columns of the 3 blocks are called stacks. And if you interchange any 2 rows in a band or any 2 columns in a stack, you get a new Sudoku puzzle, but it is essentially the same, therefore causing a symmetry of that Sudoku puzzle. And you can also interchange 2 whole bands or 2 whole stacks, which will give you the same, but essentially the same Sudoku puzzle. And if you flip it over any axis of symmetry, whether that be diagonal, vertical, or horizontal, it also creates a symmetry. These are the basic strategies when doing a Sudoku puzzle. It's called unique missing candidates, naked singles, hidden singles, and locked candidates. For the unique missing candidates, that would be when 8 out of 9 elements are in any virtual line. So if we want to go back up here, it would be if 8 of these squares would be filled rather than just 2 in that example. And then the naked singles is a strategy where you list all the possible values for a square, and you go through, and if there's only one possibility in that square during the markup, then that is called a naked single. And you can eliminate that single from any of the other blocks that it was a candidate in, or I'm sorry, not blocks, squares, and which could uncover a hidden single, which by glancing at the possibilities for that row, it then becomes a unique missing candidate. And it's also locked candidates. Once you for sure have your candidate chosen, that means it's locked, basically. To go over the algorithms and theorems based on strategies, the strategies up here that I just talked about, these four, if you use them in conjunction with each other, it does create an algorithm. However, you can use them out of order, and it will not mess up your puzzle. There's the general algorithm using the occupancy and preemptive set theorem. And they say, let X be a preemptive set in a Sudoku puzzle markup. Then every number in X that appears in the markup of cells not in X over the range of X cannot be a part of the puzzle solution. This is actually setting up a little bit of how it's connected to set theory and later on in my presentation, but it basically says that once it appears, it cannot be there, so it's occupied. I'm sorry. Then the preemptive set theorem is there's always a preemptive set that can be invoked to unhide a hidden set, which then changes the hidden set into a preemptive set, except in the case of a singleton. This means that you can make a choice, and because of that choice, you create new possibilities that weren't there before, because sometimes it just isn't a black and white solution. And this is the statement of the algorithm. You find the forced numbers in the puzzle, mark up the puzzle, and then you search iteratively for a preemptive set in all rows, columns, and boxes, taking cross-out action, as said, and that would be whenever you take a cross-out action during the unique singles and hidden singles. And if a solution is found, great, and if not, then you have to use the preemptive set theorem to make a random choice so you can continue. And the basic educational skills that come along with Sudoku puzzles in the classroom, it gives a little bit of difference than just numbers in a classroom, which students like. It teaches them about critical thinking and logic, some rational problem solving, making sure that they know their decisions are consequential. Based on the relevancy, you need to know what is relevant in a word problem. And logic is the deliberation and debate, and it's learning how or why something works rather than how something works. And it also supports creative thinking in the classroom, where you have to get creative with your guesses and sometimes even find new tactics to solve a puzzle. And it also encourages flexibility. You have to persevere because sometimes these puzzles get very hard and difficult. So it also requires discipline to keep going. And it also teaches failure, because if you're not failing, then you're not learning. Some other mathematical subjects that it relates to, it just relates to the traveling salesman problem, which is another optimization problem. It's trying to get to each city with the least amount of travel, and we want to solve the Sudoku puzzle with the least amount of decisions or time. It relates to set theory because they use the definitions of complements and sets, because the possible candidates out of all of the candidates for that possible square. And it also relates to computer science because it can include CNF coding and other ways. And to conclude, the permutation matrices and symmetries are the building blocks of Sudoku puzzles. When the strategies are used as an algorithm, it can be the most effective strategy unless the difficulty is too high, and then, of course, the general algorithm with the pre-occupancy theorem and preemptive set theorem is needed. And then Sudoku puzzles are a valuable learning tool in the classroom. And it's a new learning tool, I think, that is very good. Any questions?
Thank you, Callie. From Dr. Walters, where he's asking, do you like to do these kinds of puzzles?
I love to do these. These were my little stress reliever in my early college days.
Other questions for Callie? From Mr. McCall, did the algorithms help you with speed?
I think so. I think it taught me a little bit of having to make some guesses faster. Sometimes I would focus on not guessing and try my hardest to find obvious answers. And so I think it helped making me have to guess. And it also taught me a different way to guess. So I think so.
Okay. And I see another one from Dr. Walters. How many strategies did you study in total?
I studied just basically these two because they're called the pencil and paper algorithms. I could have studied different ones if I was more experienced in MATLAB, because I found a lot of strategies and algorithms that concerned with the CNF coding in the computer science area. So if I were to have the time, that would actually be a continuation of this project.
Okay, that's good to know. I was going to ask about future directions, and you've addressed that.
Yes, these two are the most common pencil and paper ones, while there could definitely be more strategies by using the Excel spreadsheets as well. That kind of goes with the computer science aspect.
Okay. Any other questions? Okay, it doesn't look like it. So thank you very much, Callie. Great job.
Thank you.
Rebecca will be up next. And Rebecca, you should be able to share screen. Super. Just a reminder, over in the chat, we do have the link to the Google form for you to evaluate our speakers today. And Rebecca, we'll wait just a minute or two so that we can start your presentation right at 4. Okay, Rebecca, I think it's 4, so we'll let you go ahead and get started.
Okay. Hey, everybody. My name is Rebecca Moss. My project advisor was Cassidy Jacobs. I did my project on Bridge to Bulldogs, a student in financial analysis. So today I'm going to go through an introduction of the Bridge to Bulldogs program and the questions that I posed in my project, and then I'll talk about the student data analysis, the financial data analysis, my conclusions, and future research that could be done with the Bridge to Bulldogs program. So my project was on the Bridge to Bulldogs program at Louisiana Tech University. The questions I looked to answer were, how did the Bridge students compare to general students? And also, how is the university benefiting financially from the program? Bridge to Bulldogs is an alternate route of admissions for students who do not meet all of Louisiana Tech's admission requirements. The program initially began in the fall of 2015, and it's a 2-quarter program where you take classes in summer and fall, or fall winter as a Bridge student. And students have the option of starting in the summer or fall quarter depending on their math ACT scores. If the student has a 17 in their math ACT, they have to begin in the summer, while students with an 18 math ACT in the fall. And students in the program must maintain a 2.0 cumulative GPA. They can't withdraw from classes, and they also have to attend tutoring while they're in the program. So when we looked at the data, we decided to remove the fall of 2015 data because of differences in program structure. During this quarter, the students were allowed to withdraw from classes, and they also took a different initial math course. Then we also decided to remove general students who were missing data such as ACT scores. Removing all of this data brought us to a total of 2,198 data points. There was one Bridge to Bulldogs student that we discovered took the SAT instead of the ACT, but we converted the SAT score to an equivalent ACT score. During the student data analysis, we used R to perform all of our tests, and we used the multiple linear regression model, which is represented by this equation here generally. Beta sub naught is the y-intercept, while all the beta k's are the expected change in the responsive variable, which is y, when all the remaining are held constant. Normally, multiple linear regression models are often used as predictive models, but instead of using it as a predictor, we actually use the regression approach for experimental design. So we use the linear model to determine which variables had the most significant impact on a responsive variable, which in my case, it was the overall grade received in the class. And we let each result lead us to the next logical question. One way my project advisor, Cassidy, told me to think of this is like a crime scene investigation. You let the evidence lead you to your next outcome or conclusion instead of trying to force the evidence to go to a certain conclusion. We looked at 6 factors to determine which were significant to the overall grade that was received in the course. And the 6 factors were: the student was a Bridge to Bulldogs student, the class level, the composite ACT score, the math ACT score, the course the student was in, and the quarter the student was taking the course. And in order for a factor to be considered significant, the p-value had to be less than or equal to 0.05. First, when we looked at our data, we wanted to check for normality. So we converted all grades from letter grades to numbers, with A being a 4 and F being a 0. We put the total grades here on a histogram, with the x-axis labeled as the grade that was received in the class, and the y-axis was the frequency. And as you can see here, it was somewhat normal with a skew to the left, so we decided to do the linear regression model. This was our linear model that we used, where y was the overall grade received, and each x here is the 6 factors that we talked about previously. And after coming up with the linear model, we used hypothesis test, the t-test and f-test to determine which variables were significant. And both tests had the same hypothesis used for the null hypothesis, which is where all the coefficients would be the same, and the alternative hypothesis would be that the coefficients are different. After we performed the hypothesis tests, we did computational techniques if there were differences between the 2 tests. And the computational techniques were forward selection, backward elimination, and stepwise regression. After we performed that, we also ran tests to determine if there was any multicollinearity, because if you have multicollinearity, it can lead to skewed or misleading results. And then finally, we decided to if we needed to split the data further and perform the same process that is outlined here. So then when we were running the tests, we started with all of the data together, and we found that all factors were significant except for the quarter that the students took the math class. And so since being a Bridge to Bulldog student was a significant factor, we decided to split the data into Bridge to Bulldog students and general students. So then when we compared the Bridge to Bulldog students versus the general students, the course the student was taking and the quarter the student took the course were both significant. So the quarter that the student was taking the math course, that being a significant factor was kind of a cause for concern. So we decided to look further in that direction. And since we know the difference in the atmosphere when students are taking classes in the summer and fall, we decided to split the data into the Bridge to Bulldog students who began the program in the summer and the Bridge to Bulldog students who began in the fall. Then when we compared the summer versus fall Bridge students, none of the previous factors were impacting the students' overall grade in the math courses. But we also saw that there was a difference in performance. The students who began the program in the summer were passing their math classes, while the students who began in the fall were not. So then we decided to remove all the fall Bridge to Bulldog students. So then we compared the summer Bridge to Bulldog students to the general students. Then all the factors were significant except for the quarter that the math class was taken. So now we can see that the Bridge to Bulldog student is significant regardless of the other factors that we looked at. Then we considered the fact that Math 102, 103 is the first course that the Bridge students take. So if the program is effective, we thought that any math learning deficiencies should probably be addressed during this class. So we decided to remove the Math 102, Math 103 data and look at just the future math classes. So then when we compared the summer Bridge to Bulldog students versus the general Bridge to Bulldog students, all without that Math 102, Math 103 class, we found that being a Bridge to Bulldog student was no longer a significant factor that was contributing to what the students made in their math courses. So then after looking at the student data, we wanted to also look at the financial data of the program because we wanted to see if the university was benefiting financially from the program. So during the spring and summer quarters, 5 mentors are hired, and in the summer, the mentors also receive housing and a declining balance. So we listed this as mentor expenses. There's also 2 math tutors hired during the summer quarter, which we listed here. But during every other quarter, Bridge students utilize the BART Tutoring Center. So we didn't include that pay because the BART Tutoring Center is open to any student. It's not specific to the Bridge program. In summer, we also considered faculty pay because the sections for the courses are strictly for Bridge students. And in other quarters, Bridge students are mainstreamed, meaning that they're in sections that have both Bridge and general students. So when we added all of this together, we found that the total estimated program expenses is $644,630. So that can be thought of as how much money that Tech has invested in the program so far. Because we concluded earlier that being a Bridge student was not a significant factor when we compared the summer Bridge students to the general students, we wanted to just see how much Louisiana Tech has profited strictly from the Bridge students that started in the summer. So when we looked at that data from the summer students, we found that the average retention rate was 6 quarters. So we used this average retention rate to calculate the estimated revenue. So the summer cost for Bridge students is $300 for their first summer. So we did $300 times the enrollment for each to get the summer cost. And then we used the cost of attendance for a full-time student that Tech has listed on their website, and it's listed to be $3,235 to be full-time tuition and fees. So we used that times the enrollment. And then I did the summer quarter plus 5 regular quarters would be 6 quarters of retention to get total for each summer class. Added all of those together, and it gave an estimated revenue of $2,405,350. Then using the estimated revenue from the summer bridge students and the estimated overall expenses, I calculated the estimated profit of the program to be $1,760,720. So then in conclusion, in regards to the student analysis, we found that the students who began the program in the fall were underperforming compared to the students who began the program in the summer. Also, we found that the summer British Bulldog students are performing at the same level as the general students after their initial math class, which means that they're on the same, that after that initial class, their math deficiencies have been handled. So the program is efficient and effective. In regards to the financial analysis, we found that Louisiana Tech is profiting from the program. Specifically, the program has profited an estimate of $1.7 million from the students who began in the summer alone. That doesn't take into account any fall Bridge to Bulldog students. If we were to continue this project, we would probably want to investigate the student demographics, including the major college graduation rates and overall performance, to see the long-term effects of the Bridge to Bulldogs program, particularly as it relates to the recruitment and retention of the STEM students. Because I specifically looked at their math classes, and we need to look at what colleges are gaining more of these students and what are their graduation rates as compared to the general students, and what are their performance in other classes that aren't specifically math classes. Also, we would want to refine the overall expenses, revenue, and profit even more to try to predict how much having only the summer program would affect Louisiana Tech in the future. And that concludes my presentation. I'd like to open the floor now to any questions.
Okay, great. Thank you, Rebecca. Any questions over in the chat? I was thinking, so I'll ask a quick question. I was thinking that the bridge students take like a 3-hour university seminar in the summer when they enroll as bridge in the summer. Am I remembering correctly, or is it a different class that they take with the math?
I think they take the FYE in the summer, and then they take communications in the fall, if I remember correctly.
That's what I was thinking. Yes, university seminar is the old wording. Sorry about that. So sort of a like a 3-hour FYE version.
Yeah, I think so.
Okay. So from Dr. Ming, just a comment for the other quarters, you cannot count all as profits. Dr. Ming, would you like to elaborate on that?
Yes, and I saw Rebecca was counting just multiply by those numbers, but for the other quarters when students are taking classes here at Tech, you have to count the maintenance, the overhead, and the faculty costs, right?
So it is true that there's a cost from the faculty standpoint, but it's still, those are still students who are here at the university and they're not necessarily on scholarship. In general, they are not on scholarship. So they are full tuition and fee paying students compared to some of our other students who are well funded on scholarships.
Agree. Yes, I think so. The word should be probably revenue instead of profit.
Revenue would probably be a fair way to state that.
Yes, thank you.
Any other questions for Rebecca? Okay, thank you very much. Let's see, last and certainly not least, Mark will be presenting. And Mark, I've now made you a co-host and you should be able to share your presentation with us.
All right, let me get that up.
Okay. And we are at 4:15, so we're right on time. We'll let you go ahead and get started. Okay, Mark?
All right. Sorry. All right, can y'all hear me and see my mouse okay?
Yes, we can.
All right, good afternoon, everyone. My project or my presentation involves predicting and comparing the stock value of Chick-fil-A. My project advisor is Stan McCaw. We'll go ahead and go over the outline. We're going to go over the introduction, some obstacles I ran into, some data that's needed for this project, the actual mathematical model we use, and of course the conclusions. So we'll go ahead and get started with the first part of my previous model, the free cash flow model. This was the original route we were going to take. And the free cash flow model, what it does, it allows you to predict the value or measure the value of a private company, much the same way that stock value tells the value of a publicly traded company. It tells you about the profitability and the amount of cash flow that a company has on hand. Let's go ahead and take a look at that equation. Right here, this is the original equation we were going to use. These are the variables that you would need, and I was going to do it based on population, but unfortunately, Chick-fil-A was unwilling to share this information for me, or with me, excuse me. So we ended up having to go a different route, which led us to the comparable analysis method. That was the alternate model we chose. We'll go ahead and look at that. The comparable analysis, it allows you to compare multiple companies, and through that comparison, you use ratios and relationships to ultimately derive the value of the company that you're looking for. I am going to be comparing Chick-fil-A to McDonald's and Yum Brands. Yum Brands, in case some of y'all don't know, it is the parent company of KFC, Taco Bell, Pizza Hut, and Wing Street Worldwide. I'm comparing them to these two companies because McDonald's is larger than Chick-fil-A and Yum Brands is smaller. Chick-fil-A lands right in the middle as far as sales go. So it was a good, they were good limits, sort of an upper and lower limit of what to compare Chick-fil-A to. So that's why we chose those. But we need to go ahead and look at the data needed to perform the comparable analysis. And it turns out that when you do a comparable analysis method, you need two critical pieces of data. That's market data and financial data. Market data is nothing more than trade and price data that acts as an instrument to tell a trader valuable information about a company that they may want to invest in, or perhaps that they don't want to invest in. Financial data is nothing more than financial information about a company, such as the sales, earnings, things like that. And before we actually get into it, we need to define a few terms that's going to be used throughout this method, which is the market capitalization. The market capitalization is the total dollar value for all the shares of stock that you have in circulation. So if you have a certain amount of shares in circulation and they're worth a certain value, you multiply them and that's your market capitalization. Our next one is the total enterprise value. This is a valuation tool that uses debt to measure the value of a company. If you have a company, it's everything that encompasses that company, its value minus the debt. That's your total enterprise value. The next two we're going to look at, these are actually two acronyms known as EBITDA and EBIT. These are nothing more than a measure of profitability. And they stand for earnings before interest, taxes, depreciation, and amortization. EBIT is earnings before interest and taxes. Our last one is earnings per share. That is the amount of money that a company is going to make off the shares of stock that they have in circulation. First, we're going to look at the general data for each of these corporations. We are looking at the market data and financial data. For the market data, everything is in billions of US dollars except for stock price. Financial data, everything is in billions of US dollars except for earnings per share. This right here is nothing more than the information that I acquired that we're going to use in a little bit to derive or to aid in deriving the value. The market capitalization, other than being very large numbers and telling you, it should tell you the difference in size of these two companies. This is really where we're at. It ranges from $22 billion to just over $124 billion. You can look at the total enterprise value. The sales, this also should tell you give you a good indication of their relative size. McDonald's has very large sales compared to Yum Brands. You have your EBITDA, your EBIT, and your earnings per share. This information is going to be used later, as I said, to help derive our stock value. But first, we need to look at the financial relationships. We have the market capitalization relationship and the total enterprise value relationship. What I have done, as part of this process, I took the market capitalization, I divided it by sales, I also divided it by EBITDA and EBIT. I also did the same thing for the total enterprise value. Divided that by the sales, the EBITDA, and the EBIT. Here on the end is the PE ratio, that's your price earnings ratio. And what we do here, the reason we do this, it tells you the relationship to each of these metrics that we've chosen. And if you look at them, there's two numbers for each relationship. One for McDonald's, one for Yum Brands. Most of these numbers are very, very close in value. And what I'm going to do is actually average these relationships. Let's go ahead and take a look at these averages right here. Here's the average between McDonald's and Yum Brands. I'm just going to use this first one. This is the relationship between market capitalization and sales. I could actually manipulate this and say that market capitalization on average is 4.99 times larger than the sales. Same thing goes for the EBITDA and the EBIT relative to the market cap. And look down here at your total enterprise value relationship. It's no different. This is their relationship and their ratios. And what we're going to do is we're going to use this to predict the metrics for Chick-fil-A. And before we actually get there, I want to show y'all something. I have two different values for EBITDA right here. One based off market capitalization, one based off total enterprise value. Same thing for the EBIT. One is based off market cap and the other is based off the total enterprise value. I'm actually going to derive these two values by manipulating this relationship. I can manipulate this relationship and find my EBITDA. I'm going to average those two values, and that's what's ultimately going to determine Chick-fil-A's EBITDA. Right here, I'm also going to average these two values and use that for Chick-fil-A as well. So what we did is we got the Chick-fil-A data based off this information, and I came up with the market capitalization to be a little over $63 billion. The total enterprise value was $105.63 billion. Chick-fil-A sales, which I had, was $12.78 billion. Again, close to the middle of Yum Brands and McDonald's. I got the EBITDA for Chick-fil-A and the EBIT. Now, if you notice, I have not yet gotten the stock price or the earnings per share. I had to make a few additional estimations before I could actually get there. So let's go ahead and take a look at those estimations. What I actually had to do was look at the net income. I needed the net income, but I didn't actually have that. So what I had to do, I looked at the relationship of McDonald's and Yum Brands, their relationship of the net income and the EBIT. And it turns out that McDonald's EBIT was exactly 1.5 times larger than the net income. Yum Brands was, their EBIT was 1.49 times larger than the net income. So I averaged those two to come out with 1.495. and use that ultimately to get my net income for Chick-fil-A, which was $3.31 billion. And again, as we saw a minute ago, I used the averages of Yum Brands and Chick-fil-A to get the PE ratio. Again, this just tells us that the stock price is on average 25.82 times larger than the earnings for each company. And then the last estimate I had to make was the amount of shares that Chick-fil-A would have available to their shareholders. Turns out McDonald's has 758 million shares in circulation. Yum Brands has 313 million shares in circulation. So what I did, I averaged those two values to come out with 535,500,000 shares that Chick-fil-A would have in circulation for their shareholders. And with this information, I can finally just plug and chug from here. We'll take a look at the equations. This gives me, excuse me, this gives me the earnings per share, which is the net income divided by the amount of shares. And I get $6.22 per share. That's what Chick-fil-A would make off of each share. And then I can use that variable to find the stock value, and you multiply the earnings per share times the PE ratio, which comes out to $160.60. That, ladies and gentlemen, brings me to the conclusion that Chick-fil-A's average stock value for 2019 was estimated at $160.60. I used 2019 information for everything, and that's how I came at arrived at this conclusion. To reiterate this fact again, you can see McDonald's average stock value was $198.27. Yum Brands 2019 average stock value is $104.22. So Chick-fil-A was in the middle. It was definitely closer to McDonald's than it was Yum Brands. For an additional perspective, just to show you, Starbucks sales for 2019 was $26.5 billion, and their average stock value for 2019 was $81.44. And that tells me that based on their sales was so high and this was relatively low, that they could have been more efficient. So I hope that this provides a good idea of, or a good perspective of where Chick-fil-A would land if they were a publicly traded company. And of course, here are my references. Any questions?
Okay, thanks, Mark. Great job. Any questions for Mark over in the chat box? So from Dr. Walters, as an employee, do you get an opportunity to be a private investor?
I wish, because maybe I would make a little bit more money, but unfortunately, no. I can only own one.
That's right. I recall, they wouldn't even give you the data.
Exactly. They were very stingy. They were very private with it, and they wouldn't even share it. Believe it or not, it wasn't that they were unwilling to share it with me. They were unwilling to share it with the local operator. So they are very, very secretive about their information.
Oh wow! I don't even think I realized that when we were.
Yeah,
talking.
I don't think I told you that, but my operator said no. He's like, I would get in trouble over that.
Wow. Interesting. Again, from Dr. Walters, are there any private investors that you know of?
Not to my knowledge. There's no way to really invest in Chick-fil-A, unlike McDonald's or Yum Brands or other publicly traded fast food companies. For example, you could actually purchase McDonald's. You could pay them and own your own restaurant and sell things at the price and standards that you want. You can never do that with Chick-fil-A. So to the best of my knowledge, no, there are no private investors, and there never will be.
Okay. Any other questions for Mark? Okay, well, hearing none, I just want to remind you about the Google form for evaluating the presentations. Some of you have hung through our entire Zoom room of capstone presentations. I appreciate your attention and coming out to support our students. Great job from all of our students. I think this might have been our largest group over the past 3 years that we've had senior capstone in mathematics, and I think the quality just continues to improve every year. So kudos to all. So that'll wrap up our capstone showcase. And from Mark, is it only faculty who stayed? No, I saw Callie.
Oh,
Callie
perfect.
was in here.
Okay, good.
She's gone now, but she was in here a little bit earlier.
Oh, that's great.
Yeah. All right. Well, thanks everybody. Hope you have a great weekend. Mark, you're the only student left, so I'll remind you that you need to upload your slides and your papers due next week.
Yes, ma'am. Thank you so much.
No problem. Thanks all.
All right, y'all have a good day.
All right. Bye-bye.